Hey everyone, welcome to Hadoop Crash Course by Simplilearn. In this crash course, you will learn about the most popular big data technology, that is Hadoop. For any of you out there who's new to Hadoop, not to worry, we will be starting from scratch. You will briefly understand Hadoop and the tools and the frameworks that are part of its ecosystem. For this crash course, we have our experienced instructors Richard and Ajay who will take you through the various topics of Hadoop. They will help you understand big data, Hadoop, HDFS, MapReduce, Yarn, Sqoop, Pig, Hive, and so on. You will learn all this in 4 hours with extensive hands-on demo. But before we begin, make sure to subscribe to our YouTube channel and hit the bell icon to never miss an update from Simplilearn.
We all use smartphones, but have you ever wondered how much data it generates in the form of texts, phone calls, emails, photos, videos, searches, and music? Approximately 40 exabytes of data gets generated every month by a single smartphone user. Now, imagine this number multiplied by 5 billion smartphone users. That's a lot for our mind to even process, isn't it? In fact, this amount of data is quite a lot for traditional computing systems to handle. And this massive amount of data is what we term as big data. Let's have a look at the data generated per minute on the internet. 2.1 million snaps are shared on Snapchat. 3.8 million search queries are made on Google. 1 million people log on to Facebook. 4.5 million videos are watched on YouTube. 188 million emails are sent. That's a lot of data. So, how do you classify any data as big data? This is possible with the concept of 5 V's: volume, velocity, variety, veracity, and value. Let us understand this with an example from the healthcare industry. Hospitals and clinics across the world generate massive volumes of data. 2,314 exabytes of data are collected annually in the form of patient records and test results. All this data is generated at a very high speed, which attributes to the velocity of big data. Variety refers to the various data types, such as structured, semi-structured, and unstructured data. Examples include Excel records, log files, and X-ray images. Accuracy and trustworthiness of the generated data is termed as veracity. Analyzing all this data will benefit the medical sector by enabling faster disease detection, better treatment, and reduced cost. This is known as the value of big data. But how do we store and process this big data? To do this job, we have various frameworks such as Cassandra, Hadoop, and Spark. Let us take Hadoop as an example and see how Hadoop stores and processes big data. Hadoop uses a distributed file system known as Hadoop Distributed File System to store big data. If you have a huge file, your file will be broken down into smaller chunks and stored in various machines. Not only that, when you break the file, you also make copies of it, which goes into different nodes. This way, you store your big data in a distributed way and make sure that even if one machine fails, your data is safe on another. MapReduce technique is used to process big data. A lengthy task A is broken into smaller tasks, B, C, and D. Now, instead of one machine, 3 machines take up each task and complete it in a parallel fashion and assemble the results at the end. Thanks to this, the processing becomes easy and fast. This is known as parallel processing. Now that we have stored and processed our big data, we can analyze this data for numerous applications. In games like Halo 3 and Call of Duty, designers analyze user data to understand at which stage most of the users pause, restart, or quit playing. This insight can help them rework on the storyline of the game and improve the user experience, which in turn reduces the customer churn rate. Similarly, big data also helped with disaster management during Hurricane Sandy in 2012. It was used to gain a better understanding of the storm's effect on the east coast of the U.S., and necessary measures were taken. It could predict the hurricane's landfall 5 days in advance, which wasn't possible earlier. These are some of the clear indications of how valuable big data can be once it is accurately processed and analyzed.
Here is a quick demo on setting up Cloudera Quick Start VM in case you are interested in working on a standalone cluster you can download the Cloudera Quick Start VM. So you can just type in download Cloudera Quick Start VM and you can search for package. Now this can be used to set up a quick start VM, which would be a single node Cloudera based cluster. So you can click on this link and then basically based on the platform which you would be choosing to install, such as using a VM box or which version of Cloudera you would install. So here I can select a platform, so I can choose VirtualBox and then you can click on get it now. So give your details and basically then it should allow you to download the quick start VM, which would look something like this. And once you have the zip file which is downloaded, you can unzip it, which can then be used to set up a single node Cloudera cluster. So once you have downloaded the zip file, that would look something like this. So you would have a quick start VirtualBox and then a VirtualBox disk. Now this can be used to set up a cluster. Ignore these files which are related to Amazon machines and you don't need to have that. So you would just have this, and this can be used to set up a Cloudera cluster. So for this to be set up, you can click on File, Import Appliance, and here you can choose your Quick Start VM by looking into Downloads, Quick Start VM, select this and click on Open. Now you can click on Next and that shows you the specifications of CPU, RAM, which we can then change later, and click on Import. This will start importing virtual disk image .vmdk file into your VM box. Once this is done, we will have to change the specifications of our machines to use 2 CPU cores minimum and give a little more RAM, because Cloudera Quick Start VM is very CPU intensive and it needs good amount of RAM. So to survive, I will give 2 CPU cores and 5 GB RAM, and that should be enough for us to bring up a quick start VM, which gives us a Cloudera distribution of Hadoop in a single node cluster setup, which can be used for working, learning about different distributions in Cloudera cluster, working with HDFS and other Hadoop ecosystem components. Let's just wait for this importing to finish and then we will go ahead and set up a quick start VM for our practice. Here the importing of appliance is done and we see Cloudera quick start machine is added to my list of machines. I can click on this and click on settings. As mentioned, I would like to give it more RAM and more CPU cores. So click on system and here let's increase the RAM to at least 5 and click on processor and let's give it 2 CPU cores, which would at least be better than using 1 CPU core. Network, it goes for NAT and that's fine. Click on OK and we would want to start this machine so that it uses 2 CPU cores, 5 GB RAM, and it should bring up my Cloudera Quick Start VM. Now let's go ahead and start this machine, which has our Quick Start VM. It might take initially some time to start up because internally there will be various Cloudera services which will be starting up, and those services need to be up for our Cloudera Quick Start VM to be accessible. So unlike your Apache Hadoop cluster, where we start our cluster and we will be starting all our processes, in case of Cloudera, it is your Cloudera SCM server and agents which take care of starting up of your services and starting up of your different roles for those services. I explained in my previous session that for a Cloudera cluster, it would be these services. Let me just show you that. So in case of Apache cluster, we start our services, that is we start our cluster by running script, and then basically those scripts will individually start the different processes on different nodes. In case of Cloudera, we would always have a Cloudera SCM server which would be running on one machine, and then including that machine we would have Cloudera SCM agents which would be running on multiple machines. Similarly, if we had a Hortonworks cluster, we would have Ambari server starting up on the first machine and then Ambari agents running on other machines. So your server component knows what are the services which are set up, what are their configurations, and agents running on every node are responsible to send heartbeats to the server, receive instructions, and then take care of starting and stopping up of individual roles on different machines. In case of our single node cluster setup in Quick Start VM, we would just have one SCM server and one SCM agent which will start on the machine, which will then take care of all the roles which need to be started for your different services. So we will just wait for our machine to come up and basically have Cloudera SCM server and agent running. And once we have that, we need to follow few steps so that we can have the Cloudera admin console accessible, which allows you to browse the cluster, look at different services, look at the roles for different services, and also work with your cluster either using command line or using the web interface, that is Hive. Now that my machine has come up and it already is connected to the internet, which we can see here, we need to do certain things so that we can have our admin console accessible. At this point of time, you can click on terminal and check if you have access to the cluster. So here type in host name and that shows you your host name, which is quickstart.cloudera. We can also type in HDFS command to see if we have access and if my cluster is working. These commands are same as you would give them in a Apache Hadoop cluster or in any other distribution of Hadoop. Sometimes when your cluster is up and you have access to the terminal, it might take few seconds or few minutes before there is a connection established between Cloudera SCM server and Cloudera SCM agent running in the background, which takes care of your cluster. I have given a HDFS list command, which basically should show me what by default exists on my HDFS. Let's just give it a couple of seconds before it shows us the output. We can also check by giving a service Cloudera SCM server status, and here it tells me that if you would want to use Cloudera Express free, run this command. It needs 8 GB of RAM and at least 2 virtual CPU cores. And it also mentions it may take several minutes before Cloudera Manager has started. I can log in as root here and then give the command service Cloudera SCM server status. Remember, the password for root is Cloudera. So it basically says that if you would want to check these settings, it is good to have Express Edition running. So we can close this. My HDFS access is working fine. Let's close the terminal, and here we have launch Cloudera Express. Click on this and that will give you that you need to give a command, which is force. Let's copy this command. Let's open a different terminal and let's give this command like this, which will then go ahead and shut down your Cloudera based services, and then it will restart it, only after which you will be able to access your admin console. So let's just give it a couple of minutes before it does this, and then we will have access to our admin console. Here if you see, it is starting the Cloudera Manager server again. It is waiting for Cloudera Manager API, then starting the Cloudera Manager agents, and then configuring the deployment as per the new settings which we have given as to use the Express edition of Cloudera. Once all this is done, it will say the cluster has been restarted and the admin console can be accessed by ID and password as Cloudera. We'll give it a couple of more minutes, and once this is done, we are ready to use our admin console. Now that deployment has been configured, client configurations have also been deployed, and it has restarted the Cloudera management service, it gives you an access to quick start admin console using username and password as Cloudera. Let's try accessing it. So we can open up the browser here and let's change this to 7180. That's the default port, and that shows the admin console which is coming up. Now here we can log in as Cloudera, and then Let's click on login. Now, as I said, Cloudera is very CPU intensive and memory intensive, so it would slow down since we have not given enough GB RAM to our Cloudera cluster, and thus it will be advisable to stop or even remove the services which we don't need. Now, as of now, if we look at the services, all of them look in a stop status, and that's good in one way because we can then go ahead and remove the services which we will not use in the beginning, and later we can anytime add services to the cluster. So for example, I can click on key value store here, and then I can scroll down where it says delete to remove this service from the admin console. Now, anytime you're removing a particular service, it will only remove the service from the management by Cloudera Manager. All the role groups under this service will be removed from host templates. So we can click on delete. Now, if this service was depending on some other service, it would have prompted me with a message that remove the relevant services on which this particular service depends. If the service was already running, then it would have given me a message that the service has to be stopped before it can be deleted from the Cloudera admin console. Now, this is my admin console, which allows you to click on services, look at the different roles and processes which are running for this service. We anyways have access to our Cloudera cluster from the terminal using our regular HDFS or yarn or MapReduce commands. Now I removed a service. I will also remove Solar, which we will not be using for the beginning, but then it depends on your choice. So we can here scroll down to delete it, and that says that before deleting the Solar service, you must remove the dependencies on this service from the configuration of following services, that is Hue. Now Hue is a web interface which allows you to work with your HDFS, and that is depending on this. So click on configure service dependency, and here we can make sure that our Hue service does not depend on a particular service we are removing, so that then we can have a clean removal of the service. So I'll click on none and I will say save changes. Once this is done, then we can go ahead and try removing the Solar service from our admin console, which will reduce some load on my management console, which will also allow me to work faster on my cluster. Now here we have removed the dependency of Hue on Solar, so we can click on this and then we can delete it. Remember, I'm only doing this so that my cluster becomes a little lighter and I can work on my focus services. At any point of time, if you want to add more services to your cluster, you can anytime do that. You can fix different configuration issues like what we see here with different warning messages. And here we have these services which are already existing. Now if we don't need any of the service, I can click on the drop down and click on delete. Again, this says that Sqoop 2 also has relevance to Hue. So Hue as a web interface also depends on Sqoop 2. As of now, we'll make it none. At any point of time later, you can add the services by clicking the add service option. Now this is a cluster to which you have admin access, and this is a quick start VM which gives you a single node Cloudera cluster which you can use for learning and practicing. So here we'll click on Sqoop 2 and then we will say delete, as we have configured the dependency now, and we will remove Sqoop 2 also from the list of services which your admin console is managing, right? So once this is done, we have removed 3 services which we did not need. We can even remove Sqoop as a client, and if we need, we can add that later. Now there are various other alerts which your Cloudera admin console shows, and we can always fix them by clicking on the health issues or configuration issues. We can click here and see what is the health issue it is pointing to, if that is a critical one or if that can be ignored. So it says there is an issue with a clock offset, which basically relates to an NTP service, network time protocol, which makes sure that one or multiple machines are in the same time zone and are in sync. So for now, we can click on suppress and we can just say suppress for all hosts, and we can say look into it later and confirm. So now we will not have that health issue reported, that probably the NTP service and the machines might not be in sync. Now that does not have an impact for our use case as of now, but if we have a Kerberos kind of setup which is for security, then basically this offset and time zone becomes important. So we can ignore this message and we are still good to use the cluster. We also have other configuration issues, and you can click on this, which might talk about the heap size or the RAM which is available for machines. It talks about Zookeeper should be in odd numbers. Hue does not have a load balancer. HDFS only has one data node. But all of these issues are not to be worried upon because this is a single node cluster setup. So if you want to avoid all of these warnings, you can always click on suppress and you can avoid and let your cluster be in all green status. But that's nothing to worry. So we can click on cluster and basically we can look at the services. So we have removed some services which we don't intend to use now. I have also suppressed a offset warning, which is not very critical for my use case, and basically I'm good to start the cluster. At any point of time, as I said, if you would want to add services, this is the actions button which you can use to add service. So we will just say restart my cluster, which will restart all the services one by one, starting from Zookeeper as the first service to come up. We can always click on this arrow mark and see what is happening in the services, what services are coming up and in which order. If you have any issues, you can always click on the link next to it, which will take you to the logs, and we can click on close to let it happen in the background. So this will basically let my services restart one by one, and my cluster will then become completely accessible either using Hue as a web interface or quick start terminal, which allows you to give your commands. Now while my machines are coming up, you can click on hosts and you can have a look at all the hosts we have. As of now only one, which will also tell you how many roles or processes are running on this machine. So that is 25 roles. It tells you what is the disk usage. It tells you what is the physical memory being used. And using this host tab, we can add new hosts to the cluster. We can check the configuration. We can check all the hosts. In diagnostics, you can look at the logs, which will give you access to all the logs. You can even select the sources from which you would want to have the logs, or you can give the host name. You can click on search. You can build your own charts. You can also do the admin stuff by adding different users or enabling security using the administration tab. So since we have clicked on restart of a cluster, we will slowly start seeing all the services one by one coming up, starting with Zookeeper to begin with. And once we have our cluster up and running, whether that is showing all services in green or in a different status, we still should be able to access the service. Now, as we saw in Apache Hadoop cluster, even here we can click on HDFS and we can access the web UI once our HDFS service is up by clicking on quick links. So the service is not yet up. Once it is up, we should be able to see the web UI link, which will allow you to check things from HDFS web interface. Similarly, Yarn as a service also has a web interface. So as soon as the service comes up, under your quick links, we will have access to the Yarn UI. And similarly, once the service comes up, we will have access to Hue, which will give you the web interface, which allows you to work with your HDFS, which allows you to work with your different other components within the cluster without even using the command line tools or command line options. So we will have to give it some time while the Cloudera SCM agent on every machine will be able to restart the roles which are responsible for your cluster to come up. We can always click here, which tells that there are some running commands in the background which are trying to start my cluster. We can go to the terminal and we can switch as HDFS user. Remember, HDFS user is the admin user and it does not have a password unless you have set one. So you can just log in as HDFS, which might ask you for a password initially, which we do not have. So the best way to do this is by logging in as root, where the password is Cloudera, and then you can log in as HDFS, so that then onwards you can give your HDFS commands to work with your file system. Now, since my services are coming up right now, when I try to give a HDFS command, it might not work, or it might also say that it is trying to connect to the name node, which is not up yet. So we will have to give it some time, and only once the name node is up, we will be able to access our HDFS using commands. So this is how you can quickly set up your quick start, and then you can be working using the command line options from the terminal, like what you would do in an Apache Hadoop cluster. You could use the web interfaces which allow you to work with your cluster. Now this usually takes more time, so you will have to give it some time before your services are up and running, and for any reason if you have issues, it might require you to restart your cluster several times in the beginning before it gets accustomed to the settings what you have given and it starts up the services. At any point of time, if you have any error message, then you can always go back and look in logs and see what is happening and try starting your cluster. So this is how we set up a quick start VM, and you can be using this to work with your Cloudera cluster.
Today we're covering the Hadoop ecosystem, at least the very fundamentals of all the different parts that are in the Hadoop ecosystem. And it's very robust. It's grown over the years with different things added in. There's a lot of overlapping in a lot of these tools, but we're just going to cover these basic tools so you can see what's available in the Hadoop ecosystem.
The question is, why Hadoop? Now let's understand that with an analogy. Just imagine in a town far away, Tim sells food grains in his shop. The customers were happy as Tim was very quick with the orders. And Tim sensed a good demand for other products, so he thought of expanding his business. But it wasn't easy as he expected it to be. The number of customers were increasing and he was not able to cater to their needs on time. He had to look into assisting his customers with each of their orders and billing. It was too difficult for him to manage alone. So what does he do? To start delivering orders on time and to manage the customer's demand, Tim hired 3 more people to work with him. So it was Tim, it was Matt, Luke, and Anne. Now there was still a problem. The problem was with storage area. So solutions which Tim was looking for was that he should have enough space in the shop for all the items so that he can cater to different customers for their different needs. And as it seems, storage was a bottleneck, since storing and accessing became more and more difficult with increased supply and demand. So what does Tim do? So Tim came up with an idea to overcome this issue. He basically decided to expand the storage area and distribute each category of product on different floors. Now that's a smart thinking. Customers were happy, and after picking up their products from the respective sections, the products could be built. Now if we compare this simple story of Tim to what we call as big data, let's talk in technical terms now. So we know that data has been critical and important for organizations. However, in past, data was generated at a moderate rate, and all the data was structured in nature. So when I say structured, data can have different types. Data can be structured, it can be semi-structured, and it can be unstructured. Now when we talk about structure, semi-structure, or unstructured, the main difference is presence or absence of schema. So if you can have schema defined well before the data comes in, and then your data fits into that schema, we would call it as structured. If you have intelligently defined your schema, expecting your data to get stored within that schema, however, the data pattern breaks it, then we are talking about unstructured data or absence of schema in the data. You could have semi-structured data, which basically means that you could have a mix of structured and unstructured data. Now, in past, data was mainly structured and pretty much one processor was enough to process all of it. Now, as the data generation increased, there were different types of data which were getting generated, or I would say different type of data sets which were getting generated, and that too with a high speed. So it was evidently becoming difficult for a single processor or a single machine to store, to cure, to process, to mine, to analyze different types of data and data sets. Now, with different types of data existing and they getting generated in massive amount, it posed a challenge that this data could not be processed and stored. And the known storage solutions were traditional databases. To overcome this issue, multiple processors were used. So this is where we started seeing a shift in paradigm from single processor to multiple processors, or I would say from a vertical scalable solution to a horizontal scalable solution. So when you say vertical scalability, we talk about increasing the capacity of a machine. When we talk about scalability, we mean a capability to scale, capability to expand. And when we talk about a single processor, that is vertical scalability, where you would have one machine or one server with limited amount of RAM, limited amount of storage, and you could think of expanding that by adding more RAM, adding more storage. But that would have some limits. You could not go beyond a particular limit. You probably would have to be locked in based on the vendor, because you cannot change your internal components to suit your requirements. And if we talk about horizontal scalability, that is multiple processors in this case, we are talking about adding more machines so that you could have a horizontal scalable architecture. Now, the problem which we were talking about, to overcome that issue, multiple processors were used to process each type of data. And here we see a similarity in Tim's approach with the technical approach of going for a distributed platform which could handle huge amount of data coming in different formats, data getting generated with a lot of speed, and thus helping the organization. Now what happens is, when you think of having multiple solutions or having multiple systems which can be used to store or process your data, one of the major challenge is one storage system being accessed by all the machines becomes a bottleneck. And that is again a problem, similar to what Tim was having when he decided to cater to multiple customers looking for different products, but then he was limited with the storage space he had and to keep all the products in one place. So just like how Tim adopted the distributed approach, the storage system, which was a bottleneck, was also then distributed. So in this way, your data could be stored in individual databases or in individual machines on their disks. However, it could be accessed from one place. So if we look at this story, we see two approaches. And these two approaches are the ones which are used by Hadoop, which is a framework. And these approaches are your storage layer, that is your HDFS, and your processing paradigm, that is MapReduce. Now, what is HDFS? Let's understand this. HDFS stands for Hadoop Distributed File System. So that's a logical storage layer. It's a distributed storage space, just like our example of Tim having distributed the storage space amongst various sections. So each person was taking care of a separate section, and at the end, the customers went to the cashier for the final billing. This sorted the process and made it easier. Now this is how similar, or this is how Hadoop MapReduce works. Now that was a rough story of big data generation and why Hadoop is required, right? Let me explain what Hadoop is. So if we talk about what is Hadoop, it's basically a framework. It's not a programming language. It's not an architecture. It's not just a hardware. It's not just a software. It is a framework which allows you to store and process big data in a distributed and parallel fashion. Now there are a lot of users which have made big data case study a famous and a popular one. So here are some companies, say Facebook or Instagram, Google, Twitter, LinkedIn, Skype, YouTube, and many more. And these and many more organizations across the globe are using Hadoop for their storage and processing requirements. However, it would not be just Hadoop. Hadoop also comes with its own ecosystem, which has various set of open source technologies and packages, all packaged together to help an organization in various facets of its data life. So the question is, how does Hadoop store and process all of this data? Or I would say this big data. Or before we even talk about Hadoop, which has individual components which are responsible for storing and processing big data, we also need to understand what is big data. So big data is just a term. Data has been exponentially growing in past decade, and now we don't talk about gigabytes or terabytes. We already are talking about petabytes and exabytes, or even zettabytes, that is 10 to the power 21 bytes. However, in known fact is any organization is not processing zettabytes of data, but yes, there are organizations which are processing petabytes and exabytes of data. So how does Hadoop help them? And what is this big data? So big data is a term coined to explain the data which is very complex, which is huge, which is getting generated with a lot of speed, which has a lot of variety, and then it becomes a challenge to store, to capture, to analyze, process this data, and derive useful information out of it. Now we are talking about huge amount of data. We are talking about different V's, that is V for volume, V for velocity, V for variety, V for veracity, and other aspects like viscosity, validity, virality, and many more. So when your data comes in with all these characteristics, it can be easily categorized as big data. And organizations in recent past have realized that they cannot ignore any data considering it as uneconomical. So they would want to work on all of it. And when I say all of it, that is one of the drawbacks in terms of RDBMS. So in RDBMS, usually you will never have 100% of data online. You would still have your data. It would be consistent. You could do transactions, but you would not have access to all 100% of it because that would be a costlier option. So in RDBMS, you would have 10 or 20 or 30% of data which would be online, and rest of the data would be archived, which basically means that if you would want to process that data, you would have to bring it from the storage layer to the processing layer, process it, and then store it back. Now, how does Hadoop help in this approach or this requirement? So when we talk about components of Hadoop, we have a storage layer, that is HDFS. Now, you can compare this with your own laptop or PC. Every laptop or a PC has two layers. It has a storage layer, that is your disk or your external hard disk, which is attached to your machine, and your machine also has the processing layer, which is your RAM and CPU cores. So HDFS is the storage layer of Hadoop. So it's a logical storage layer, which technically speaking does not exist, but then yes, it exists because it depends on the individual file system of multiple machines. We'll learn about this in a few minutes. The other layer is the processing layer. So when you talk about MapReduce, it is a programming model which allows you to process the data in one particular way. Now MapReduce has been oldest and the most mature. So when I say most mature, it has evolved over time. Since the time Hadoop came into existence, MapReduce exists. It is still being used by organizations for doing processing. And when we talk about processing here, we are not talking about processing on one single machine, but we are talking about processing on multiple number of machines where each machine's RAM and CPU cores contribute to the processing. So we have two main components. One is your HDFS, one is your MapReduce. And for your MapReduce or basically any other processing framework, MapReduce is one of them. So for any other kind of processing, say massive parallel processing, say graph processing, say MapReduce processing, say structured query language being processing, for all of these processing needs, there is a processing layer called YARN. Now YARN stands for yet another resource negotiator. So basically YARN takes care of your resource management. That is, when the processing happens across the machines, who would take care of RAM and CPU core which would be required for processing, and that would be your YARN. Let's learn a little bit more on the storage layer, a distributed file system which belongs to Hadoop. So Hadoop distributed file system is known for its distributed storage method. Well, it derives its functionality, or would be say is inspired based on Google file system, wherein you would have your data stored across multiple machines. So HDFS also distributes the data among many computers or many machines. Let's take a simple example here. Take an example of you working on your profile or your resume and you would like to go to your friend's place. Now you have two options. One, content in a pen drive. Take the pen drive with you, go to your friend's place, plug in the pen drive, and voila, there you have your file. The second approach is you can have your file uploaded to a Dropbox or basically attached to your mail and save it as a draft, and you could be at your friend's place opening up your mail and reworking on your document or your resume or your profile. Now in this example which I just mentioned, for you, your Yahoo Mail or your Dropbox or some other web site where you are uploading your document is like a logical storage layer. Well, you are uploading your document, but that document is not getting stored within your mailbox. It is basically getting stored on the underlying servers, which are being used by Yahoo or Dropbox or basically any other social media website. So for you, you have a storage layer which allows you or gives you the feel that your data just exists for you to access it. However, that data is residing on one of the underlying machines or servers which the service provider has. So similarly, when you talk about HDFS, it is a logical storage layer which distributes the data among multiple machines. So for user, it is a storage layer where you can write your data. You could be writing your data to HDFS, you could basically create a copy of it, and you could do many other things with your data, and your data gets stored on HDFS, but technically speaking, it gets stored on the disks of lot of underlying machines. And in addition to this, whatever data gets stored on the underlying machines is auto-replicated to some other machines so that you never have loss of data. Now here we see that we are talking about block of data which is stored. So if you would have a file which you would want to store in a Hadoop cluster, now when I say cluster here, I mean multiple machines plugged in together to serve a functionality. So if you would be writing in a file, depending on the size of file, the file would be split into blocks. We'll learn more about that. So as of now, you can understand that the file would be split in blocks, and the blocks will be distributed across your underlying machines, and each block which gets stored on one underlying machine is also having its replica or multiple replicas across different machines. So if we talk about a 500 MB of data which is getting stored in a traditional method, we would say this is how your 500 MB data would get stored. So you would have entire data that is getting stored in one database or underlying file system, right, which may overload the database, which may overload the file system, and the fault tolerance is pretty much zero. So if your database crashes, if your storage layer crashes, if your file system is not accessible, then you lose all of your data. So this is more of a data sharing architecture where you say that the data is getting stored in underlying database or underlying file system, and then it is being shared or accessed by multiple applications or multiple users. If we talk about Hadoop's storage layer, that is HDFS, the problem is taken care because the data is distributed across multiple machines. So if we look at this image, it explains that the same 500 MB of data which was getting stored in one location in a standard solution would now be getting stored across machines so that one single machine is not overloaded, and second, you have your data distributed across multiple machines. And as I mentioned earlier, your data is split in blocks, and each block is replicated again on different machines. So that gives you an idea that even if one or a couple of machines fail, you would not have a complete loss of data. Or in fact, I would say you would have no loss of data because your data has replicas existing on some other machines. So HDFS is actually designed for storing massive data sets in commodity hardware. Now, when we say commodity hardware or commodity machines, we mean something which is not as big or as powerful as a carrier class hardware, but it's not even as small or less powerful as your simple desktop or laptop. So commodity machines is basically machines which have good amount or mediocre amount of RAM and CPU cores, and then you could have multiple of these used to set up your cluster, and that would be serving your distributed file system. Now HDFS again has two main components, or I would say this logical layer is functional with two different processes or two different components which would be running on different machines. So you have a name node and you have a data node. So as we see, name node, as it says, it is something to do with name, and data node is something to do with data. So name node is the master of the system, or I would say master of your cluster, master of your storage layer, that is HDFS, and it basically stores all the metadata. So that already explains that name node is really critical because it stores the metadata. It is the master, which basically also means that if your name node crashes or the machine where name node process is running, if that machine crashes, then you would have no access to your cluster. So there are a lot of ways in which that could be made highly available. There are concepts of high availability. There is a concept of federation, which basically allows having more number of master machines to make your cluster more stable and also to store your metadata in multiple locations. Data node is the slave machine or the slave node, or I would say slave process, which is running on one or multiple machines. Now here we are talking about horizontal scalability. So name node being the master would be running on one machine or multiple machines depending on the setup, such as high availability or federation. However, data node, which is the slave node, would be running on multiple machines. The more number of machines you have, the better. More number of machines you have, it would give you more scalability, more processing capacity, and more storage capacity. So data nodes are the ones which are taking care of your read-write operations, and they are the ones which are storing the actual data. So which basically means if I have a cluster of 10 machines and my one machine is master, which is name node, then I can have data nodes running on all the 10 machines if I would want my data to be stored across all the 10 machines. However, the best planning strategy would be that you would have name node running on one single machine and you would not have data nodes competing with name node for resources and storage. So in a cluster of 10 machines, I could have one name node and 9 data nodes. That means the disk of these 9 data nodes are contributing their storage for HDFS. Or I could say another way that whenever you write data to HDFS, your data would be actually getting stored in the underlying data nodes or 9 of these data nodes. Let's go further. Now, if you see here, it also explains your interaction between your slave and master. Now, name node is a master, so it's not name node's responsibility to ping every machine and check if it is available. In fact, it is other way. Your data nodes are sending signals or heartbeat every 3 seconds to the name node. So as soon as your cluster comes up, as soon as you start your cluster, you would have name node running on one of the machines and data nodes running on multiple machines. And as soon as the cluster comes up, data nodes will start sending packets of information to name node so that name node can register the information of which data nodes are available in the cluster. Now, this initially is only from data nodes to sending heartbeat to name node, registering their information, confirming their availability. So the actual data is getting stored in data nodes, and data is in the form of again a logical entity called blocks. So the default size of each block is 128 MB, and that started with Hadoop version 2. So prior to Hadoop version 2, we had the default block size 64 MB. However, there is no limit. You can, on the other side, you can have, whether it is Hadoop version 1 or Hadoop version 2, your block size could start with the default size, and then they could even go to gigabytes, terabytes, petabytes level. However, in organizations, you would always observe that the default block size is 128 MB. So if we talk about this 530 MB file, it's very obvious that it cannot get stored in one block. Now this file would be split into multiple blocks. So let's imagine your file 530 MB is being written to HDFS, and it would get split into 4 blocks. Each block can contain up to 128 MB data. So my block A would have 128, block B would have again 128, block C would have 128 again, and block D would have 128. So we are talking about 256 plus 256. That basically makes it around 512, which would not be enough for your 530 MB file. That's why we would need one more block of 128 MB, which could hold the rest 18 MB data. So that's how your file would be split and stored in multiple blocks. And remember, each block which would get stored on a data node would have a replica of itself on two other data nodes. So the default replication is 3 and the default block size is 128 MB. Both of these parameters can be customized. So you can set your block size to something else. You could set your replication to something else. However, the default is replication as 3 and block as 128. So to store a file of 530 MB, you would need at least 5 blocks. And if I say replication is 3, then I would technically have 15 blocks getting stored across machines. Now, if we see this part, the last block, it says 18 MB. So remember one thing, your block is just a logical entity. So for a file of 1 kilobyte or 127.99 megabytes, it would still use a block of 128 MB, which does not mean there is a space wastage. Block is just a logical entity to take your data to the disk. So when you write, imagine you write a file of 1 kilobyte on HDFS, it would call in for a block of 128 MB. The block then gets stored on the underlying disk. And when it gets stored on the underlying disk, it will only use 1 kilobyte of disk space. And if we consider replication, then you can say 3 kilobytes of disk space across machines. Now that's how your HDFS works. Your data could be stored, either all the blocks could be stored on data node 1 and then they could have their replicas on data node 2 and data node 3, or randomly when your blocks are distributed, you could have all the blocks spread across multiple machines and then their replicas would be existing on other machines. So the first rule of replication, just to mention here, is that any particular block would not exist with its replica on the same node. Or I could put it in a different way. I could say you will never ever have two blocks which are identical getting stored on the same data node. Now all these blocks are getting stored in data nodes. Now what happens if the block or the node containing block A crashes? So do we lose the data because the underlying machine has gone? And that's the beauty of HDFS, that we have something called as auto replication. And that is mainly to give you more fault tolerance. That is mainly to prevent the loss of data. So if one particular machine goes away, we already know that this block A would have replica existing on two other machines, and you can have your data accessed from one of these machines in the cluster. So the user doesn't have to worry if a particular machine has crashed or gone away, provided the data was replicated and it was stored across multiple machines. Now, I could also say that if you had enabled replication as 1 and you did not have copies of your blocks, and if the data node containing the block crashed, then potentially you have a chance of losing your data or not being accessible because you did not enable replication or you did not set the replication to more than 1. Now, your HDFS is smart enough, or I would say NameNode is smart enough to handle your data node failures. So what HDFS offers is auto replication feature. Any data which is being written to HDFS, depending on its size, would be existing in one or multiple blocks, and each of those blocks are automatically replicated across your machines on the cluster. And if a particular data node, or if I have a replication of 3 and within this, if I lose 2 machines holding my block and its replica, then I still have the third machine where one more replica exists, which potentially gives me a chance to get back my data. I don't need to worry about any kind of data loss. So this is how it would look. So if you have block A, which is getting stored on data node 1, and we also have the concept of rack here, which we can talk later. So you would have the same block A having its replica on 2 other machines, and that could be, those 2 machines could be belonging to a different rack. So you have the replication achieved here because block A exists with 2 other copies. Now, one point to remember here is in Hadoop or in HDFS, you don't have any difference between original block and a replica of it. It basically means the same. All of them have the same power or status. Now, if you talk in terms of rack awareness, that is, if you have a cluster where machines are placed in racks. Now, what are racks used for? So in organizations, racks are a systematic and a logical way of keeping your machines together. So you could have different kind of setups. You could have one rack holding all the machines which have only master processes running, or you could have other option of each rack having a machine with a master process and rest machines would be slave processes. Now, whichever aspect we talk about, if your machines are placed in rack, then the second rule of replication kicks in. Now, what was my first rule of replication? You will never have two identical blocks sitting on the same machine. So block A and a copy of block A cannot be existing on data node 1 or 2 or 3 or any of this. Now when we talk about machines being placed in rack, and if your name node is made aware of it, if your cluster is made aware of it based on configuration, then the second rule of replication kicks in, which basically means you will never have a block and its replicas all residing on the same rack, even if they satisfy the first rule. So even if you would say, well, my block D is having its replicas on some other machines, and I would want to have all these machines in one rack. Well, you could do that, but that does not give you a redundant solution. There can be other solution also, as we see here, where your block 2 is spread across 3 different racks, and that's okay, but that's not preferable because then you're increasing your bandwidth requirement. So the rule of rack awareness, or how the blocks are placed, if your cluster is rack aware, is that you will have something like what we see for block B or block A, where you would have block B on data node 4 and its replicas on some other rack on 2 different machines. So even if one rack is lost, you still don't lose your data because there are copies of that block existing on some other machines on some other rack. So this is how replication in HDFS offers fault tolerance, and it basically gives you the flexibility of working with the cluster without being bothered of which of the underlying machine is not performing well or is not available. So that's about your name node and data nodes and your blocks being placed. Remember, your block size can be customized, your replication can be customized, and that basically would apply at a cluster level. Let's now spend some time in understanding the architecture of HDFS, that is basically your Hadoop distributed file system, how it works, and how do these different components contribute to the functionality of HDFS. Now what we have learned is that name node is the master of your cluster, and it's also master of your storage layer, right? So name node basically takes care of storing metadata of the cluster in its RAM and also in its disk. How does that happen? So when a particular cluster starts, you would have your data nodes coming up and also your name node coming up. And as we discussed earlier, your data nodes will start sending heartbeat to name node every 3 seconds as soon as they have come up. So data nodes are sending their heartbeat to name node, and name node has started registering this information in its RAM. So this is the first kind of metadata which name node has in its RAM. Now name node also has some metadata in disk which would have been created when before starting your cluster you would have done some formatting. So usually when you would want to set up a cluster, you would basically have the Hadoop related packages downloaded on all the machines, which would have Hadoop related directory. It would have a config directory where you would have your config files, and based on that you would have decided that some of your machines would run data nodes and then which machine would be having name node running. So in the beginning, when the cluster is about to be started, the first thing which is done is a formatting, and that formatting actually creates metadata in the name node's disk. Now this metadata contains your file system image, that is what does your Hadoop cluster or file system contain before even it is started. It has basically the identifiers of the cluster such as namespace ID, cluster ID and block pool ID, and all this information name node has in its disk. So name node cannot come up if this metadata in disk does not exist. So once the metadata in disk exists, you can go ahead and start the cluster, and that's where your data nodes will send heartbeat within 3 seconds of coming up to the name node, so that name node starts registering this information in its RAM. So that's the first metadata which name node has in its RAM. So as I mentioned earlier, your racks are basically available in organization because they would want to store their machines in a systematic way, and your racks could have machines where your master process would be running or your slave processes such as your data nodes would be running. So if you have racks available, then the replication would make sure that the blocks would be placed in such a way that you would never have a block and all its replicas on the same rack. So with the machines placed in racks, the rack placement policy makes sure that all the replicas, as I mentioned, will not be existing on the same rack. Now that is when you have racks. So if a client has a read request, it will always first contact the name node, checking that it is interested in reading a particular file and where can it find this file. Now name node basically checks the metadata in RAM because it initially has information of your data nodes which are available, but not only that, if there was data written earlier to the data nodes would also be sending every 10 seconds the block report to the name node. So as soon as the data nodes come up, they send their heartbeat, making name node aware about their availability, and when the data was written to HDFS, data nodes would be also sending their block report every 10 seconds to the name node. And this is additional metadata which name node is storing in its RAM. So basically name node has information of what are the data nodes available, what are the files which are written to the cluster, the files are split in which blocks, the blocks are sitting on which data nodes, and what are the file permissions. So whenever a client would want to read some data, it would contact name node. Name node would look into its metadata and then it will respond back with a ordered set of data nodes where the replicas or the blocks can be found. Now once the client gets this information, your client can read the data from the underlying data nodes. Now that's how a read is happening, and this would happen in a parallel fashion from multiple data nodes. When it comes to write, it is a similar process that if a client would want to write some data, it would contact name node. Name node would give a list of data nodes which are available where the data can be written, and then basically client would write the data directly to these data nodes. So in this fashion, your HDFS basically handles the read and write where name node is an important component. Now these are some of the features of your HDFS. So as I mentioned earlier, HDFS offers fault tolerance because of the multiple copies of data which are existing across data nodes, and that is due to the auto replication feature which HDFS has. When it comes to data security, your HDFS provides end-to-end encryption that protects the data. Scalability wise, since we have multiple underlying nodes which can be used for your read and write, and also you can add any number of nodes to the cluster, which basically makes scalability one of the features of HDFS. When it comes to flexibility, Hadoop is flexible in storing any type of data. As I mentioned, it can store structured, semi-structured, and unstructured data, and data which is getting generated in huge volume and with a lot of velocity. So these are some of the features of HDFS which makes it an appropriate solution for storing huge amount of data with an intention that you would want to read, write huge amount of data, and also process that data for your different business requirements. Now that we have stored our data in HDFS, what's the purpose? Any organization would want to store huge amount of data with an intention that they would want to process it. And for processing, Hadoop has its programming model, that is MapReduce. Now, MapReduce is one of the oldest and most mature processing programming model, which is little rigid. It is batch oriented operation, but then it allows you to process huge amount of data which is spread across your cluster. So if we compare traditional approach, big data was processed at the master node, or it is still master node is one which is playing an important role. So your slave machines or your data nodes are the machines where your data is actually getting stored. Now, like your HDFS as the storage layer, you also have a processing layer called yarn. So in case of HDFS being the storage layer, you have name node as the master and data nodes as the slaves. In the same way, for your processing layer, resource manager is the master and node managers are your slaves. And node managers would be co-located with data nodes. So if you would want to process huge amount of data from multiple machines, how would you do that? And that's where MapReduce comes in handy. So if data has to be processed, there has to be some mechanism where instead of moving your data from the storage layer to processing layer, you would want to process the data wherever it is stored. Now that is an approach which MapReduce uses. Hadoop has this data locality reference, which basically means do not move the data from one layer to other layer, but process the data wherever it is actually stored. So let's understand what is MapReduce and how it works. So as I mentioned, it's a programming technique. It's a programming model. However, it does not depend on one specific programming language. So you can have your MapReduce programs written in Java or Python or Scala, any programming language. So it's a programming technique. It's a programming model where huge amount of data is processed in parallel and in a distributed fashion. So when you talk about MapReduce, as the word itself says, it has basically two phases. One is your mapping and one is your reducing. So mapping phase is taken care by a mapper function provided by the developer. Reducing phase is taken care by a reducer function, which is again provided by the developer. And these mapper and reducer functions internally run map and reduce tasks. So if you would want to understand this better, let's look at this. So for example, you have your data stored on HDFS. Now we know that depending on the size of data, it would be split and stored in the form of blocks across your machines. Now for your map and reduce, the first thing is the input data has to be divided in the form of input splits. So by default, your each split is equal to the block size. Or I could tell this in a simpler term that if your file has 2 blocks, it would mean that your MapReduce or your map task has to work on 2 splits, each block being one split or one chunk of data on which the processing would start. So as I said, your mapping phase is basically something which has your mapper function, and mapper function would have the code for map task which would run on one or multiple split. So each split has to be processed, and then there is an intermittent result which is your output from mapping phase. Now this data might be coming in from one map task or multiple map tasks. So basically there would be some kind of shuffling and sorting wherein the output of mapping phase is then grouped together so that it could be further processed. Then we have our reducing phase, which depends on the reducer function, and this reducer function does the reduce task of working on one or multiple inputs coming from the output of map phase. So reducing does the aggregation and finally creates a final output. So here if you look at this, your mapper function is provided by the developer, which takes care of your mapping tasks. Your reducer function is again provided by the developer, which takes care of reducing tasks. Your sorting, shuffling, also we have partitioning, which decides how many reduced tasks would be used. All that is taken care by the framework itself. Now looking further, let's see how MapReduce works with an example. So this is my input data, which is basically one line, or you can say 3 lines, which has to be processed. So we have input data which says welcome to Hadoop. Hadoop is interesting. Hadoop is easy. Now this could be split. Imagine that this data is huge, probably more than 128 MB. So imagine this file would be then split into multiple blocks, each block acting as a split, some portion of data being in every block. So these are your input splits. So imagine this file is split, and then you have welcome to Hadoop as one split, Hadoop is interesting as other split, and Hadoop is easy. So these are the input splits which will have to be worked upon by your mapper function. So your mapping phase, where your mapper function would work on each split, would consider every line as a record. Now remember, Hadoop has different formats. So the default format is text format. However, Hadoop supports your input format in different ways. So the main task of your mapper function or the map tasks is to work on every record or work on every split and convert that into list of data elements which are nothing but key value pairs. So if we take an example of a traditional word count where we would want to count the words in a file, your mapper function would basically look at every record. It will break each record into list of elements, that is words here, and with every word we have one, the value given to every word. So here we have the word as the key and the value is 1. Now this is the output from your mapping phase. But if I want to do a word count, this is obviously not my final output. So what happens next? So once your mapping phase complete, this data then has to be shuffled and sorted so that the similar keys can be brought in together. Now that would obviously help the further phases. Now once the sorting and shuffling is done, you would have this data being handled by reducing phase. Now, before it goes to reducing, you might hear something about partitioning phase, which basically decides on the keys how many reduced tasks might be required to work on this. So here we see our type of keys are words. So we could easily assume that there would be one reduced task which would work on this shuffled and sorted data. And your reducing phase can then aggregate all the keys which are similar and count the values or increment the values. So your final output would be again a list of elements which are nothing but words and their total count which we wanted to do. So when you talk about your MapReduce, it has good load balancing. So you have map and reduce tasks. Now remember, your map tasks have to complete before the reduce tasks could start. Now the data being split is done by framework. The splits are being worked upon my map tasks, and your reduce tasks would then work on the output of map tasks. Now there is also something called as re-execution of tasks. So for example, if a task map or reduce fails on one of the machine, your MapReduce programming model doesn't give up. So you would have a re-execution of the tasks on either the same node or on a different node, and all that re-execution and everything is taken care by the processing layer yarn. So it's a simple programming model, but yes, we have to agree it is little rigid because whatever processing you do using MapReduce has to follow mapping and reducing paradigm. It's one of the simplest programming language which is based on Java, but as I mentioned, it can also be coded in any other programming language. So if we talk about HDFS, it's a storage layer. MapReduce, it's a programming model, and both of them were and are important units in Hadoop. So with Hadoop version 1, there was a limitation. So the MapReduce version 1 was a kind of limitation. Now the limitation was in the way the processing was handled. So in case of Hadoop version 1, the processing layer had a master called job tracker, and then you had your slaves called task trackers. But the problem was that job tracker was not only responsible for doing resource management or resource allocation, but it was also taking care of job execution. Now that was a problem because in this case, job tracker was overburdened because it was listening to all the task trackers, it was tracking their resources, and it was taking care of processing. So if a task failed, then it was the work of job tracker to basically restart or re-execute that task on some other machine. Now that sounds like a drawback. So job tracker being overburdened was kind of a bottleneck. Now in Hadoop version 2, yarn was introduced. So yarn, being a processing layer, can support different kind of processing frameworks. So in Hadoop version 1, the only kind of processing we could do is MapReduce, and no other processing was possible. But from Hadoop version 2 onwards, with yarn being introduced, we can and we could do different kind of processing on top of your Hadoop clusters. So what is yarn? As I mentioned in the beginning, yarn stands for yet another resource negotiator. Now that is something which brought more powers to your Hadoop clusters. So when we talk about yarn, it is a resource management layer or the processing layer of Hadoop. Now we discuss HDFS is for storage, MapReduce is one of the ways to process the data, but who takes care of the resource allocation? Who takes care of negotiating the resources across your cluster on multiple machines? And that is what yarn specialization is doing. So yarn, the processing layer, has a master which is called resource manager. Now this is replacement to the master in Hadoop version 1, which was called job tracker. So your resource manager at a higher level, you could say, manages the assignment of resources such as CPU, memory, and your disk. Node manager are your slave processes. Now this is a replacement of task tracker in Hadoop version 1. And remember, node managers would be co-located with data nodes. So if we have 10 data nodes, you can easily understand that there will be 10 node managers running on the same machine wherever data nodes are running. The new or the another negotiator which we talk about is application master. So it's a simple piece of code which runs whenever an application is submitted and whenever resource manager has already negotiated resources with node manager. So how does this work? Now let's imagine a client would want to do some processing. Now here we should remember that the client would have already interacted with name node, getting an information of which machines are available, where the data exists, and where the processing could be done. Name node would have internally responded back with the information that the data which client is interested in lies on XYZ data nodes. Then your client contacts the resource manager. Now resource manager, which is the master, is keeping a track of the resources which node managers have. So every node manager is like a worker process which has some allocated amount of resources. So for example, we can say that if every machine had 10 CPU cores and 20 GB RAM, then say some percentage of those resources would be allocated to node manager on every machine to take care of your processing. Node managers are not only sending heartbeat, but they are also communicating their resources to resource manager. Resource manager is the one which is listening to the client and is also tracking the resources which node managers have. Now whenever a particular client wants to do some processing, your resource manager will make a request to node managers for resources. So for example, if your application needs 6 GB of RAM and 4 CPU cores, your resource manager could be requesting these resources to node manager. So for example, here in this case, your resource manager will negotiate the node manager 1 for 3 GB RAM and 2 CPU cores, and similarly 3 GB RAM and 2 CPU cores to the second node manager. So this request of holding resources which will be used for processing is called container. So instead of we calling every time resource manager asking for RAM and CPU cores, we could easily say resource manager requests a container of some size. Container definitions are already defined in the yarn configuration file. So once resource manager requests these containers, node manager, depending on the load what they have, depending on the resources they have, will communicate back to resource manager about their approval on these containers. Now once the container is granted, or once the node manager has promised that it can give the container to resource manager will start an application master. So here we should remember application master is a temporary daemon which will run only till the application executes, which also means for every application which is submitted to the cluster, you would have one application master. So what does this application master do? Application master would basically use this container and it will get the execution of application done. So the question is, where does this application master run? So from the requested containers, your application master would also run in one of the containers that is in some amount of RAM and CPU core, and it will use the other containers for getting the execution done on the machines wherever the relevant data resides. So this is what happens. So your client program sends an application request to resource manager. Resource manager is already getting an information of which nodes are available, what is their capacity, how much resources they have, and so on. Resource manager would then, based on the job request or application request, contact the node manager requesting for containers. Node manager grants the request, and then your resource manager would start application master, basically saying take care of the execution, and once the execution of application is done, come back and communicate to me. Application master, which is a piece of code, will run in one of the containers and will use all the other containers to execute the tasks. Now here we should remember one thing. Resource manager, being the master, is the only one which can negotiate or ask for containers to node managers. At any point of time, if an application master needs more container, for example, a node manager or a machine crashes, an application master cannot use the container on that particular node. In that case, application master will always contact the main master, that is resource manager, to negotiate more resources. Your application master cannot directly request resources to node manager. Now that is what happens in Yarn. So Yarn has an internal component called scheduler, which takes care of job scheduling. So Yarn is responsible to process your job request and allocate resources which are required. With this capability of Yarn having an application master, which is a temporary daemon, Yarn supports multi-tenancy, which basically means different kind of processing can now happen on Yarn, which also means we can have multiple users which would be using the cluster, and you could even have different versions of MapReduce or other processing framework possible on Yarn. Now, when we talk about scalability, when we talk about our cluster, we would already know that there can be huge number of nodes, and those nodes can be dynamically added to the cluster, which basically gives us a possibility of a scalable processing layer. Now, so that basically tells us one thing, that Hadoop is a solution which companies would want to use if they would want to process big data, if they would want to store big data. And many companies are already using Hadoop. So when we talk about Hadoop, there are many other solutions in the market which would compete or mention that they could do it better than Hadoop, or they could do what Hadoop is doing. And that's not false. However, the success stories of Hadoop are quite a lot, because Hadoop has been in the market for quite some time and it is being used by various companies. So when we talk about companies, there are different companies. You can always look at huge list of companies by just typing in Google companies using Hadoop. One such use case is about Pinterest. So you might have heard of the popular image sharing website called Pinterest. Now this is how it would look. So you have different categories here, and it basically offers you different kind of images. So Pinterest is a social media platform which allows you to pin any interesting information you find on its website. Think of the traffic, think of people who would be visiting this website, think of the user related data or usage related data that would be getting generated. So Pinterest has more than 250 million users and nearly 30 billion pins. All these account to big data concerning Pinterest. And as I said, it's not just about providing a functionality. You would have a lot of users logging in. You would have user related data, probably their behavior related data, probably how website responds to different users, and these different pins on about which customers find something interesting. So the problem here was Pinterest faced a challenge in processing tremendous amount of data. And as I mentioned, this is not just a case of Pinterest. There are a lot of companies which are working with big data or are interested in working with big data. And the biggest challenge is storing this data and processing this data when the data volume is huge. So if you would want to store or continue capturing or curing or mining or analyzing this big data, and if you would want the data which needs to be displayed in users' personalized discovery engine, that would certainly be a problem. What was the solution? Hadoop. Hadoop, with its features like HDFS, which allows you scalable storage, auto replication, fault tolerance, and flexibility to scale with a processing layer such as Yarn, makes it available for an organization like Pinterest, which could not only store huge amount of data but also could easily process this data. So Pinterest uses Hadoop to process and analyze big data in a way that it helps the company to show the most relevant content to its users. And that's a win situation for a company which started using Hadoop. Now, through continuous analysis of the data, Pinterest can provide its users with features such as related pins, guided search, and so on. Now, this is how Pinterest benefited from Hadoop. So, one of the recommendations here is, if your organization or if you would want to work on so-called big data, if your interests are in storing, curing, capturing, mining, processing, and analyzing huge volume of data, which contains a lot of variety, which gets generated with a lot of speed, which has other characteristics like viscosity, validity, virality, volatility, you should be using big data. So I would suggest let's start using Hadoop and put an end to the big data challenges which we might be facing in absence of a solution such as Hadoop. Let's also look at a quick demo on using HDFS, MapReduce, and Yarn, which will clear our concepts on HDFS, MapReduce, and Yarn. Now that we have set up a 2-node cluster, which has 2 data nodes, 2 node managers, 1 master machine, let's try working with HDFS. Let's look at quick commands which allow you to write data to the cluster, although there are different ways. The first way is using commands. The second is using an IDE, and where you could write your code to use Hadoop's file system API. And the third is a graphical user interface called Hue, which normally does not come with Apache. Although it can work with Apache, it comes as a service with Cloudera and other distributions. To work with HDFS, we need some sample data. Now there are various websites from where you can get some sample data. So you can open up your browser and let me show you some sample places or sample data set links from where you can download bigger or smaller files, which then can be used to write data to your HDFS. Although you could just pick up a local file, or you could create your own files and write them to HDFS. There are various dataset sites which can be used. So for example, you can type in machine learning UCI datasets, and this is one link which has more than 200 datasets, which can be used for even data science kind of activities, which can be used for testing with your algorithms, and you can download data from here onto your local machine, and then from your local machine we will be writing the data to HDFS, which then based on the size of the data splits the data into blocks, and your blocks would get stored on your underlying machines wherever data nodes run. So I can click on this UCI machine learning repository, or even just on data sets to be very specific. All we need is some sample data sets. You can get Kaggle data sets, you can get data sets from Yelp website, which are bigger data sets zipped, and you can be using them to write data to see how your file split into multiple blocks. Now here we have a lot of data. We can click on any one link to begin with, and here I have the data folder, shows me the some file, and I can just right click on this, save link as, and save the file. This is a simple text file and we can save it. And you can get various data sets from here. You can even go to Yelp dataset challenge, and that has bigger files which are zipped and they can be downloaded. So you can click on download dataset. Although I will not start the downloading here, you can just give in your name here, just some email ID, some initials, and you can click on download. So this is one more website where you can download the JSON datasets, which are 3.6 gigabytes in compressed format, and then you have photos which are in 7.2 gigabytes. You can also say Gutenberg download books, and that is again a website from where you can download free datasets which are not very huge. So try to get some variety of datasets in different formats, which then you can write to HDFS. You can even use your HDFS log files which already exist on your machines, and you don't need to download anything from internet. Now let's close this for now. So I already have some file. Let's copy this from home, HDC, downloads. That was my file. Let's copy it to home HDC, and here's my file. I can check the permissions. So that's owned by HDC. I can even look into user local Hadoop logs, and there are some already log files. So you can even copy some of these files using copy user local Hadoop logs, and let's take Hadoop data node related log, and let's copy it to home SDC for our testing. And now we have some other files. Now to work with HDFS, as I said, you can always type in HDFS and that shows you various options. Now we already used the first option, which is name node hyphen format. We also used HDFS admin to look at how many nodes we have, and to work with your HDFS file system, the option is DFS. So you would say HDFS, DFS, and then you can always hit on enter, which shows you various options to work with your distributed file system, like creating a directory, copying some files, getting data from your HDFS to your local machine, changing the permissions, changing the replication, and many other options. So here, let's click on HDFS, DFS. Let's create a directory and let's call it my data. So this is a directory I'm creating on HDFS. Remember, this directory will not be seen on your local machine. It is a HDFS directory. Now, if I look in my root, I don't see my data because that's a HDFS directory, which is technically getting created on HDFS. And once you start writing data to HDFS, the relevant blocks will start getting stored under ABC/data. So as of now, we can always keep a browser open to see, as we work with HDFS, how does the data propagate or come to your distributed file system using the web interface. So here, let's say http://m1.5.0.0.70, and that's my browser interface. Let's click on utilities and let's click on browse the file system, which should show the directory which we have created, although that does not have any data as of now. Let's go in here. And now we know that we have some files here. So I will say HDFS, DFS, and this has two options. Either I can say put or I can say copy from local. Both of these do the same thing, and both of these you can find here. So we have put and we should have copy from local. That is, you're copying the data from your local machine to your HDFS. So now I will say copy from local. I will say take the ABA directory or file and put it in my data. So now I'm technically copying a file from my local file system to my HDFS, which is then using again my local file system's path. So this is done. Let's quickly check by clicking on my data if my file is written. Now if you see, this file is 187 kilobytes. However, this will still use a block of 128, and in my previous sessions I already explained why a block of 128, but when it goes to the disk, it will only occupy the space for the data the block has. We can quickly go in here and we can do a HDFS DFS listing of my directory, which should have my file now, and we can quickly check if my file is replicated either using the web interface, which says replication is 2. That means the file related blocks should be getting stored on the underlying data nodes. We can always click on overview if we would want to browse and scroll down, which says there are 3 files and a directory. The file has 1 block, so totally you have 4 file system objects. We can scroll down to show or see we have 2 live nodes, and if you see, each node has 1 block. We can always look from our data path by looking into ABC/data/current, that has block pool directory, that has current, that has finalized, that has subdirectory, and the block. Look at the size of the block. It is 191, which relates to the kilobyte size which we are talking about. Similarly, we can check on M2 machine, which also has a data node running, to make sure our file related block is replicated. So look in block pool, current, finalized, subdirectory, and that shows me the same block which is replicated with its meta file and with the same size. This ensures that my data is getting replicated as per whatever factor we have set, and my file is written to HDFS. And now I can also do a complete listing. I can just say a recursive listing to show me all the directories and all the files which I have in my HDFS. I think we are forgetting something. We are logged in as root. which is not right. So we need to be logged in as HDC, and then we can try our commands, that is HDFS DFS-ls / which should show me my directory. But then if you would want to do a recursive listing of showing all the directories and files, you can just add -r. So we have written a file to HDFS in my data directory. Similarly, I can write using a put command. Last time we used a copy from local. I will use a put command. I will say, let's take this log file and let us write it to the my data directory. Instead of copy from local, I'm using a put command, which also allows me to write the file to my HDFS. Once this is done, let's go to the web UI and let's go to browse the file system. Let's look in our directory, and that shows me that I have a log file which is even smaller than the first file which we wrote. It is in kilobytes. However, it is replicated. It is using still the block size, and we can always go back and look at the terminal to see if for my new file I have a new block which should be in my data path. And if you see this is my block, which will also have a replication on machine 2. So this is how you write one file, or you could write multiple files. Let's create some files here. So I have these log files. Let's say Hadoop log, and let's give it a name like this. So now if you see, I just created multiple files, and I can also say HDFS DFS make directory, let's say my data 2. So I'm creating a new directory on my HDFS, and then I can even copy multiple files or a complete directory. So all I need to do here is give a matching pattern or a directory. So I'll say HDFS DFS put, and then I can say take all the directories of files and put it to my data 2. Remember, this one file or multiple files are following the replication what has been set at a cluster level. Now if we do a recursive listing where I would want to see all the directories and the files which are within my HDFS, I see that I have a my data directory, and I also have a my data 2 directory which has multiple files, and all of the files within the directory are following the replication set at a cluster level. So all of them are having their blocks replicated twice. We can always go back here. We can just do a back, and that shows me what I have in my data 2. Everything is replicated twice. What I have in my data is also replicated twice. Now HDFS also has a functionality where you can write data with a different replication. So let's create one more directory, and now let's write data with a different replication. So the way I write my files, I follow the same thing. However, now I will say -dfs.replication, and I will specify it as 1. So I'm passing in as argument, and I'm specifying that I would want to write data with a replication of just 1. So my blocks will not be considered under replicated, and I'm choosing to write these files in this directory with a replication of 1. We can check from our browser interface by just doing a quick refresh. And here, if I click on my data 3, it shows it follows a replication of 1. There is also a command to check your replication status using HDFS. So we can say HDFS fsck/files/blocks, and if I would want to see only blocks or only files, I could choose one of them. Now here I have given a complete HDFS file system. I can replace that with /my-data. So I can say my data 3. This is what I would want to see, and this will show me within this directory how many files I have, how many blocks does each file use, and is it replicated correctly. So my fsck command gives me an information that in my data 3 I have one file which is 24 kilobytes, uses one block because it is very smaller than 128, and it is replicated only once. So there is no situation of over under misreplicated blocks. We have our files correctly replicated as they were specified while writing. Same thing can be seen for other files, say mydata2, and that will tell me that all the files within mydata2 were replicated as per the default replication, which was at a cluster level. And if you see here, everything is replicated twice. We don't have any over, under, misreplicated blocks, and my file system status is healthy. So this is the HDFS command to make sure that your files are replicated correctly. So we have seen how your files are written with default replication. We have seen how your files follow a dynamic replication, what you specify on the command line. Now we can also see a command which allows us to change replication after the data has been written. So I can say set rep, and I can say path, that is my data 3, where I initially had all my file related blocks replicated only once, and now I'll say my data 3, and I can specify that this should follow a replication of 2, which basically means that it will look into the directory, it will check all the files which had only one block, and now it will create a replica of those blocks across other data nodes. We can always go back and look into the data node logs to see the replication happening. We can also look from the browser interface, which initially was showing a replication of 1, and now it shows a replication of 2. So this is the command to change the replication after the data has been written. So our writes can have default replication. We can write files with a different replication. We can change the replication after the data is written. Not only that, we can even get the data from our HDFS to my local machine. And for that, I'll give HDFS get command or copy to local. So I can say my data 3, and then I can bring it to my local machine in home HDC using a get command. So this is to get data from your HDFS to your local machine using a HDFS command. Now if you see, I should have a my data 3 directory which is in my local path, and we can look in my data 3. It has all the files which we had on HDFS. So we were not only putting data from our local machine to HDFS, we also successfully brought data from our HDFS to local machine. We have written data with different replication. We have checked the status of nodes. We have checked the status of blocks, and if we would want to delete some data, HDFS also has options for that. So I can say HDFS DFS remove, and I could also do a recursive remove to remove everything including the directory from my data 3. So this will delete data from my HDFS. However, if thrash is enabled, now thrash basically means recycle bin, which depends on a property in the core-site file. We have not enabled it. If thrash is enabled, then your data will be deleted from HDFS. However, it will not be permanently deleted. It will sit in thrash for a time interval what admin has specified in the configuration file. So right now I deleted thrash, and this seems to be gone from HDFS because we have not set up any thrash. However, if a thrash is set up, then either you can decide to have your data deleted and still be in thrash so that it could be restored, or you could delete it permanently using a skip thrash option. However, remember, this skip thrash option makes more sense if the thrash is enabled in your cluster and you do not want your deleted data to be sitting in thrash even for whatever time interval has been set. Because even if the data sits in thrash and your thrash is a directory structure on HDFS, all the data will still be replicated. So we have seen how you can write data to the cluster, how you can get data from cluster to your local machine, how you can write it with different replications, how you can delete it from your cluster, and do a recursive listing of your directories and files. Now there are various other commands which can be used. For example, something like copy or move or change permissions and many more. So the more you would want to try, type in HDFS DFS, and that shows you different options which can be used to practice working with HDFS using commands. Now that we have looked at understanding MapReduce, understanding HDFS and Yarn, let's have a quick demo on a simple MapReduce program which could give me a total count of URLs or websites which were most frequently visited. Now for that, I have a sample file here and I would be using those. So if you look into my file, this basically has a list of URLs and some counts already, although we have some URLs which are repeated. Now you could have a huge list of URLs from either a script or a basically different program which has given you an initial count of the URLs which were visited by users in different locations or in different sites. And what we would want to do is we would want to work on such file and get a total count of URLs based on users who have visited these URLs. So what I would want is to look into a huge file which has list of URLs and a count for each URL, but then I would want to have a cumulative count of user visits for a particular URL so that I can find out which URL was the most popular one and which URL was least visited. So let's take this as an example. Now for that, if I would want to use a MapReduce approach, I would need a mapper class which does the map task, and here we have our mapper class which imports basically some packages which will be used by my code. I have my mapper class called URL count that extends mapper and it expects data in particular data types which are Hadoop specific, that is text, int, writable, and so on. And here we would be interested in working on the file where we would try to get the key and value out of the file. Now our key would be the URLs and value would be the initial count which shows up in the file. Now what do I need? I also need a reducer which basically will do a aggregation. And what does this do? This will overall look at all your key value pairs, and based on the keys it will aggregate the values if the key is repeated. Now this is my map and reduce, but then I also need a driver program which basically would tell me what is my mapper class, what is my reducer class, what would be my output key format, and what would be my value format. And also in the configuration I am setting a property which will allow me to read key value pairs wherein they are separated by space as a delimiter. Now once you have your code written, that is your driver program, your mapper, and your reducer, you can basically export this into a jar file, and here I could just select the project and then it shows that this is the location where I would want to save my jar file. I can just say finish. If it already exists, it will ask me to overwrite it, and I'm okay with that. Now once your jar file is ready, we also need to closely remember what is the package we are using and what's my class name. Now once you have your jar file, you also need the file existing on your HDFS so that you can do MapReduce. Now let me just log into a cluster here, and that's my login details. I will just paste the password and hit enter. So I'm on web console, and if I do a listing, I see that there is the jar file which I just created, and there is also a url.txt file. Now here we can look into this url.txt file, and that has some data here. Now we can add some more data if we would want to look at different URLs. Let's say if users have visited Yahoo, especially the mail part of it, and then I will say might be 20 times. Then you had Yahoo being visited from a different location, and that was 3 times. You have say people visiting google.com and let's say Gmail here, and I would say 12 times. Let's say again google.com/Gmail from a different location, and that was 4 times. Let's say http:// and let's say url1.com, and that was visited again 8 times recently, and so on. So now this is my sample file, and what I would do is I will just put it on HDFS in this particular location. I'm using a -f option because the file already exists and I'm just trying to put the updated one. Now once this is done, we are good to run our MapReduce, which will look into these list of key value pairs, which are nothing but URLs, and a count of users visiting these URLs. So for this I can say Hadoop jar and then I need to mention my jar file which has my class, and my package name is this one, and then my class name was this one. Now I need to give an input, so I will say user my directory, and within my directory I have a file called url.txt, and I would want my output also, so I will specify my directory, and then let's say url output, and let's call it 1. So this will be the directory which will be created, which will have the result of my MapReduce on this file, which should give me a cumulative count of how many times a particular URL or a website was visited. Now let's run this. So this is basically submitting your MapReduce job to a yarn cluster. We could also run MapReduce in a local mode. Now we see it is connecting to resource manager. It will first go through the mapping phase. Now here we have only one file to process, so it basically went for one map task, and then it would go for one reduce task. Now if we also look in, this will tell me what was the map input record, so each line is considered as a record, and when we say output records, it has broken down that into list of unique values. Now that becomes an input to your combiner phase if in your driver program you have mentioned a mini reduce, that is your combiner. If none, then the output of your map becomes the input of your reduce phase, and reduce finally gives me the list of URLs and their count. Now since my job has completed fine, I should be able to look at my output directory, which is this one, and whenever a MapReduce runs, depending on the number of reduce tasks, we would have one or more part files created as an output. So let's have a look at this. What does my output contain? So if I say HDFS DFS minus ls, that will show me how many part files I have, and if there is one part file, it basically confirms that there was one reduce task which was running and which has given me the output. Now we can choose this one, which is part-r 1, 2, 3, 4, 5, and let's do a cat to see how does my MapReduce output look, and let's have a look what it has done. And if you see here, depending on the URLs which were existing in the file, might be multiple entries of the same URL which were visited by users in different location, my MapReduce has looked at the URLs as the key, the count of those URLs as the values, and has given me a cumulative count of how many times a particular URL was visited. And if I see here, the highest count for URL 1 says that that was the website which was mostly visited by users across different locations. And if we look at URL 11, that is the least, which is visited by the users. So this is a simple example of MapReduce where we created our own code, where we wrote our own mapper, reducer, and driver program. We packaged it as jar, and then we ran it over a cluster. Now at the same time, if I would want to look at my job which has run, I can always go to the resource manager UI. Now that could be from an Apache cluster or from a Cloudera cluster or Hortonworks cluster, and we could always click on yarn as a service in terms of Cloudera or Hortonworks. In terms of Apache, you would have to manually go to your resource manager UI. Now since my application completed successfully, I can look for it in history server. So when I click on history server, it shows me the URL count. So that is what we had specified in my driver program, that my job would be called URL count. And here I can look at this one, which shows me that there was one map task and one reduce task which ran. Well, we can always go and look into the logs to see more details if we are interested in, and we can click on full log, which can then give me a detailed information of what happened when the job ran, on how the container was allocated, how the container moved from request to being initiated to being used to being released. We can always look into the log here. Now we can also go back here and we can just look at the map task. So it tells me this is the map task which ran, and it basically, if you click on this, it tells me so it ran on a particular node which is 10.2, and we can always look at task specific logs. And similarly, we can also look for the reduce task which completed, and if you click on the task, it shows you which node was used for our job. So if we had a really huge file, we could have multiple map tasks, Or if we had similar files placed in a directory, then our directory could be input for MapReduce to give us the count. Now there are a lot of traditional examples of MapReduce. You can always search on GitHub. You can always look on your cluster for the default programs. So for example, here in Cloudera cluster, we have opt, Cloudera, parcels, cd, h, lib, Hadoop, MapReduce, and then I can search for MapReduce related jar files. For example, this is the one which exists, or I can always look into Hadoop, MapReduce, just do a complete listing. And that shows me we have, say, Hadoop MapReduce client. So this is all also something which can be used. So we could just look in this one, and if you would want to see what are the programs or what are the classes already available in these jars, all you need to do is just go here and say Hadoop jar, and that shows me all the programs which are part of this jar file. Similarly, we could have looked for Hadoop MapReduce examples, and here I could look at all the programs. So there is a traditional word count program which is existing in this jar file, and if you would want to run this, then or any of these programs, you would have to specify your input or out. So this is a quick demo on your MapReduce where we have not used a default one, but we have written our own code to solve our own use case of looking into a particular file which has URLs with their count of visits, and then we would want a cumulative count by doing a MapReduce kind of processing to list down all the URLs which were most frequently accessed and URLs which were least accessed by the users. So before we look into the demo on how Yarn works, I would suggest looking into one of the blogs from Cloudera. So you can just look for Yarn Untangling, and this is really a good blog which basically talks about the overall functionality which I explained just now. So as we mentioned here, so you basically have the master process, you have the worker process which basically takes care of your processing, your resource manager being the master and node manager being the slave. This also talks about the resources which each node manager has. It talks about the Yarn configuration file where you give all these properties. It basically shows you node manager which reports the amount of resources it has to resource manager. Now remember, if worker node shows 8x8 CPU cores and 128 GB RAM, and if your node manager says 64 vCores and RAM 128 GB, then that's not the total capacity of your node. It is some portion of your node which is allocated to node manager. Now once your node manager reports that, your resource manager is requesting for containers based on the application. What is a container? It is basically a logical name given to a combination of vCore and RAM. It is within this container where you would have basically the process running. So once your application starts and once node manager is guaranteed these containers, your application or your resource manager has basically already started an application master within the container. And what does that application master do? It uses the other containers where the tasks would run. So this is a very good blog which you can refer to, and this also talks about MapReduce. If you have already followed the MapReduce tutorials in past, then you would know about the different kind of tasks, that is map and reduce, and these map and reduce tasks could be running within the container in one or multiple. As I said, it could be map task, it could be reduce task, it could be a Spark based task which would be running within the container. Now here we can also give a yarn command. So let me just clear the screen and I will say yarn, and that shows me different options. So apart from your web interface, something like web UI, apart from your yarn's web UI, you could also be looking for information using yarn commands here. So these are some list of commands which we can check. Now you can just type in yarn and version if you would want to see the version, which basically gives you information of what is the Hadoop version being used and what is the vendor specific distribution version. So here we see we are working on Cloudera's distribution 5.14, which is internally using Hadoop 2.6. Now similarly, you can be doing a yarn application list. So if you give this, that could be an exhaustive list of all the applications which are running or applications which have completed. So here we don't see any applications because right now probably there are no applications which are running. It also shows you could be pulling out different status such as submitted, accepted, or running. Now you could also say I would want to see the services that have finished running. So I could say yarn application list and app states as finished. So here we could be using our command. So I could say yarn application list, and then I would want to see the app states, which gives me the applications which have finished. And we would want to list all the applications which finished. Now that might be applications which succeeded, right? And there is a huge list of application which is coming in from the history server, which is basically showing you the huge list of applications which have completed. So this is one way. And then you could also be searching for one particular application. If you would want to search a particular application, if you have the application ID, you could always be doing a grep. That's a simple way. I could say basically let's pick up this one, and if I would want to search for this, if I would want more details on this, I could obviously do that by calling in my previous command, and you could do a grep if that's what you want to do. And if you would want to search, is there an application which is in the list of my applications that shows my application? I could pull out more information about my application. So I could look at the log files for a particular application by giving the application ID. So I could say yarn logs. Now that's an option. And anytime you have a doubt, just hit enter. It will always give you options what you need to give with a particular command. So I can say yarn logs application ID. Now we copied an application ID and we could just give it here. We could give other options like app owner, or if you would want to get into the container details, or if you would want to check on a particular node. Now here I'm giving yarn logs and then I'm pointing it to an application ID, and it says the log aggregation has not completed. Might be this was an application which was triggered based on a particular interactive shell or based on a particular query. So there is no log existing for this particular application. You can always look at the status of an application. You can kill an application. So here you can be saying yarn application, and then what would you want to do with an application? Hit and enter. It shows you the different options. So we just tried app states. You could always look at the last one which says status. And then for my status, I could be giving my application ID. So that tells me what is the status of this application. It connects to the resource manager. It tells me what's the application ID, what kind of application it was, who ran it, which was the queue, where the job was running, what was the start and end time, what is the progress, the status of it, if it is finished or if it has succeeded. And then it basically gives me also an information of where the application master was running. It gives me the information where you can find this job details in history server if you are interested in looking into. It also gives you a aggregate resource allocation which tells how much GB memory and how many core seconds it used. So this is basically looking out at the application details. Now I could kill an application if the application was already running. I could always do a yarn application minus kill, and then I could be giving my application. Now I could try killing this. However, it would say the application is already finished. If I had an application running and if my application was already given an application ID by resource manager, I could just kill it. I can also say yarn node list, which should give me a list of the node managers. Now this is what we were looking from the yarn web UI, and we were pulling out the information, so we can get this kind of information from your command line. Always remember and always try to be well accustomed with the command line. So you can do various things from the command line, and then obviously you have the web UIs which can help you with a graphical interface, easily able to access things. Now you could be also starting the resource manager, which we would not be doing here because we are already running in a cluster. So you could give a yarn resource manager. You could get the logs of resource manager if you would want by giving yarn daemon. So we can try that. So you can say yarn and then daemon. So it says it does not find the daemon. So you can give something like this, get level, and here I will have to give the node and the IP address where you want to check the logs of resource manager. So you could be giving this, for which we will have to then get into Cloudera manager to look into the nodes and the IP address. You could be giving a command something like this, which basically gives you the level of the log which you have, and I got this resource manager address from the web UI. Now I can be giving in this command to look into the daemon log, and it basically says you would want to look at the resource manager related log, and you have the log4j which is being used for logging. The kind of level which has been set as info, which can again be changed in the way you're logging the information. Now you can try any other commands also from yarn, for example looking at the yarn rm admin. So you can always do a yarn rm admin, and this basically gives you a lot of other informations like refreshing the queues or refreshing the nodes, or basically looking at the admin ACLs or getting groups. So you could always get group names for a particular user. Now we could search for a particular user such as yarn or HDFS itself. So I could just say here I would want get groups, and then I could be searching for say username HDFS. So that tells me HDFS belongs to a Hadoop group. Similarly, you could search for say MapRed, or you could search for yarn. So these are service related users which automatically get created, and you can pull out information related to these. You can always do a refresh nodes kind of command, and that is mainly done internally. This can be useful when you're doing commissioning, decommissioning. But then in case of Cloudera or Hortonworks kind of cluster, you would not be manually giving this command, because if you are doing a commissioning, decommissioning from an admin console, and if you are an administrator, then you could just restart the services which are affected, and that will take care of this. But if you were working in an Apache cluster, and if you were doing commissioning, decommissioning, then you would be using in two commands: refresh nodes, and basically that's for refreshing the nodes which should not be used for processing. And similarly, you could have a command refresh nodes which comes with HDFS. So these are different options which you can use with your yarn on the command line. You could also be using curl commands to get more information about your cluster by giving curl -x and then basically pointing out to your resource manager web UI address. Now here I would like to print out the cluster related metrics, and I could just simply do this, which basically gives me a high level information of how many applications were submitted, how many are pending, what is the reserved resources, what is the available amount of memory or CPU cores, and all the information. Similarly, you can be using the same curl commands to get more information like scheduler information. So you would just replace the metrics with scheduler, and you could get the information of the different queues. Now that's a huge list. We can cancel this, and that would give me the list of all the queues which are allocated and what are the resources allocated for each queue. You could also get cluster information on application IDs and status running of applications running in yarn. So you would have to replace the last bit of it, and you would say I would want to look at the applications, and that gives me a huge list of applications. Then you can do a grep, and you can be filtering out specific application related information. Similarly, you can be looking at the nodes. So you can always be looking at node specific information, which gives you how many nodes you have. But this could be mainly used when you have an application which wants to, or a web application which wants to use a curl command and would want to get information about your cluster from an HTTP interface. Now, when it comes to application, we can basically try running a simple or a sample MapReduce job, which could then be triggered on yarn, and it would use the resources. Now I can look at my application here, and I can be looking into my specific directory, which is this one, which should have a lot of files and directories which we have here. Now I could pick up one of these and I could be using a simple example to do some processing. Let's take up this file. So there is a file, and I could run a simple word count, or I could be running a Hive query which triggers a MapReduce job. I could even run a Spark application which would then show that the application is running on the cluster. So for example, if I would say Spark to shell. Now I know that this is an interactive way of working with Spark, but this internally triggers a Spark submit, and this runs an application. So here, when you do a Spark to shell, by default it will contact Yarn, so it gets an application ID. It is running on Yarn with the master being Yarn, and now I have access to the interactive way of working with Spark. Now if I go and look into applications, I should be able to see my application which has been started here, and it shows up here. So this is my application 3827 which has been started on Yarn, and as of now we can also look into the Yarn UI, and that shows me the application which has been started, which basically has one running container which has one CPU core allocated, 2 GB RAM, and it's in progress, although we are not doing anything there. So we can always look at our applications from the Yarn UI, or as I mentioned, from your applications tab within Yarn services, which gives us the information, and you can even click on this application to follow and see more information, but you should be given access to that. Now this is just a simple application which I triggered using Spark shell. Similarly, I can basically be running a MapReduce. Now to run a MapReduce, I can say Hadoop jar, and that basically needs a class. So we can look for the default path, which is opt Cloudera parcels cdh lib Hadoop MapReduce Hadoop MapReduce examples, and then we can look at this particular jar file, and if I hit on enter, it shows me the different classes which are part of this jar. And here I would like to use word count. So I could just give this, I could say word count. Now remember, I could run the job in a particular queue by giving in an argument here. So I could say -d mapred dot job dot queue dot name, and then I can point my job to a particular queue. I can even give different arguments in saying I would want my MapReduce output to be compressed, or I want it to be stored in a particular directory, and so on. So here I have the word count, and then basically what I can be doing is I can be pointing it to a particular input path, and then I can have my output which can be getting stored here, again a directory which we need to choose, and I will say output new, and I can submit my job. Now once I've submitted my job, it connects to resource manager. It basically gets a job ID, it gets an application ID, it shows you from where you can track your application. You can always go to the Yarn UI, and you can be looking at your application and the resources it is using. So my application was not a big one, and it has already completed. It triggered one map task, it launched one reduce task. It was working on around 12,466 records, where you have then the output of map, which is these many number of output records, which was then taken by a combiner, and finally by a reducer, which basically gives you the output. So this is my Yarn application which has completed. Now I could be looking into the Yarn UI, and if my job has completed, you might not see your application here. So as of now, it shows up here, the word count which I ran. It also shows me my previous Spark shell job. It shows me my application is completed, and if you would want further information on this, you can click and go to the history server if you have been given access to it, or directly go to the history server web UI where your application shows up. It shows how many map and reduce tasks it was running. You can click on this particular application, which basically gives you information of your map and reduce tasks. You can look at different counters for your application, right? You can always look at map specific tasks. You can always look into one particular task, what it did, on which node it was running, or you can be looking at the complete application log. So you can always click on the logs, and here you have click here for full log, which gives you the information, and you can always look for your application, which can give you information of app master being launched, or you could have search for the word container. So you could see a job which needs one or multiple containers, and then you could say container is being requested, then you could see container is being allocated, then you can see what is the container size, and then basically your task moves from initializing to running in the container. And finally, you can even search for release, which will tell you that the container was released. So you can always look into the log for more information. So this is how you can interact with Yarn. This is how you can interact with your command line to look for more information, or using your Yarn web UI, or you can also be looking into your Hue for more information.
We're going to start getting into the tools because you had all those pictures of all those cool tools we have. So we're going to look at the first two of those tools. And in the tools we have Sqoop and Flume. And this is for your data collection and ingestion. We're going to bring Spark up in just a second. Can also play a major role in this because Spark is its own animal that's sprung from Hadoop, connects into Hadoop, but it can run completely independent. But Sqoop and Flume are specific to Hadoop, and they're ways to bring in information into the Hadoop file system. And so when we talk about these, we'll start with Sqoop. Sqoop is used to transfer data between Hadoop and external data stores such as relational databases and enterprise data warehouses. And so you can see right here, here's our Hadoop data, and it's connecting up there, and it's either pushing the data or pulling the data. And we have our relational database and enterprise data warehouse. And there's that magic word enterprise. That means these are the servers that are very high end. So maybe you have a high-end SQL server or a MySQL server or whatever over there. And this is what's coming and going from the Sqoop. It imports data from external data stores into the HDFS, Hive, and HBase. Those are our two specific. The Hive setup is your SQL basically. And you can see a nice little image here. Here's somebody on their laptop, which would be considered the client machine, putting together their code. They push the Sqoop. The Sqoop goes into the task manager. The task manager then goes, hey, what have I got for the HBase and Hive system in our Hadoop system? And then it reaches out to the enterprise data warehouse or into the document-based system or relationship-based database. Relationship is your non-SQL. Document is just what it sounds like, is you have HTML documents or Word documents or text documents, and it's able to map those tasks and then bring those into the Hadoop file system. Sqoop Import. So here we have our RDBMS data store, and we have the folders on there. So maybe it's your company's database, maybe it's an archive at Google with all the searches going on, whatever it is. Usually you think with Sqoop, you think SQL, you think MySQL Server or Microsoft SQL Server, that kind of setup. So it gathers the metadata, and you see the Sqoop import. So introspect database to gather metadata, primary key information. And then it submits. So you can see submits map only job. Remember we talked about MapReduce? It only needs the map side of it because we're not reducing the data, we're just mapping it over. Sqoop divides the input data set into splits and uses individual map tests to push the splits into HDFS. So right into the Hadoop file system. And you can see down on the right is kind of a small depiction of a Hadoop cluster. And then you have Sqoop export. So we're going to go the other direction. And with the other direction, you have your Hadoop file system storage, which is your Hadoop cluster. You have your Sqoop job, and each one of those clusters then gets a map. The mapper comes out to each one of the computers that has data on it. So the first step is you've got to gather the metadata. So step one, you gather the metadata. Step 2, submits map only job. Introspect database to gather metadata, primary key information. Sqoop divides the input dataset into splits and uses individual map tests to push the splits to RDBMS. Sqoop will export Hadoop files back to RDBMS tables. And you can think of this in a number of different manners. One of them would be if you're restoring a backup from the Hadoop file system into your enterprise machines. There's certainly many others as far as exploring data and data science. So as we dig a little deeper into Sqoop input, we have our connect, our JDBC, and our URL. So specify the JDBC connect string. Connecting manager, we specify the connection manager class to use. You can see here driver with the class name, manually specify the JDBC driver class to use. Hadoop MapReduce home directory, override Hadoop mapped home, username, set authentication username, and of course help, print usage instructions. And with the export, you'll see that we can specify the JDBC connect string, specify the connection manager class to use, manually specify JDBC driver class to use. You do have to let it know to override the Hadoop MapReduce home, and that's true on both of these, and set authentication username, and finally you can print out all your help setup. So you can see the format for Sqoop is pretty straightforward, both import and export. So let's continue on our path and look at Sqoop processing and what the computer goes through for that. And when we talk about Sqoop processing, first Sqoop runs in the Hadoop cluster. It imports data from the RDBMS, the NoSQL database, to the Hadoop file system. So remember, it might not be importing the data from a RDBMS, it might actually be coming from a NoSQL, and there's many out there. It uses mappers to slice the incoming data into multiple formats and load the data into HDFS. It exports data back into an RDBMS while making sure that the schema of the data in the database is maintained. So now that we've looked at the basic commands in our Sqoop and the Sqoop processing, or at least the basics as far as theory is concerned, let's just jump in and take a look at a demo on Sqoop. For this demo, I'm going to use our Cloudera Quick Start. If you've been watching our other demos we've done, you'll see that we've been using that pretty consistently. Certainly this will work in any of your Horton Sandbox, which is also a single node testing machine. Cloudera is one of them. There's a Docker version instead of VirtualBox, and you can also set up your own Hadoop cluster. Plan a little extra time. If you're not an admin, it's actually a pretty significant endeavor. For an admin, if you've been adminning Linux machines for a very long time and you know a lot of the commands, I find it for most admins it takes them about 2 to 4 hours the first time they go in and create a virtual machine and set up their own Hadoop. In this case though, when you're just learning and getting set up, best to start with Cloudera. Cloudera also includes an install version of MySQL. That way you don't have to worry about installing the SQL version for importing data from and to. Once you're in the Cloudera Quick Start, you'll see it opens a nice CentOS Linux interface, and it has the desktop set up on there. This is really nice for learning, so you're not just looking at command lines. And from in here, it should open up by default to Hue. If not, you can click on Hue. Hue's a kind of a fun little web-based interface. Under Hue, I can go under Query, I can pick an editor, and we'll go right down to Sqoop. So now I'm just going to load the Sqoop editor in our Hue. Now I'm going to switch over and do this all in command line. I just want to show that you can actually do this in Hue through the web-based interface. The reason I like to do the command line is specifically on my computer, it runs much quicker. Or if I do the command line here and I run it, it tends to have an extra lag or an added layer in it. So for this, we're going to go ahead and open our command line. The second reason I do this is we're going to need to go ahead and edit our MySQL so we have something to scoop in. Otherwise, I don't have anything going in there. And of course, we'll zoom in this and increase the size of our screen. So for this demo, our hands-on, I'm going to use Oracle VirtualBox Manager and the Cloudera Quick Start. If you're not familiar with this, we do have another tutorial we put out, and you can send a note in the YouTube video below and let our team know and they'll send you a link. Or come visit www.simplilearn.com. Now this creates a Linux box on my Windows computer, so we're going to be in Linux, and it'll be the Cloudera version with Sqoop. It will also be using MySQL. MySQL Server. Once inside the Cloudera VirtualBox, we'll go under the Hue editor. Now we're going to do everything in terminal window, but I just want you to be aware that under the Hue editor, you can go under Query, Editor, and you'll see as we come down here, here's our Sqoop on this. So you can run your Sqoop from in here. Now before we do this, we have to do a little exploration in MySQL or MySQL Server. That way we know what data is coming in. So let me go ahead and open up a terminal window. In Cloudera, you have a terminal window at the top here that you can just click on and open it up. And let me just go ahead and zoom in on here. We'll go View and Zoom in. Now to get into MySQL Server, you simply type in MySQL, and this part will depend on your setup. Now the Cloudera Quick Start comes up that the username is root and the password is Cloudera. Kind of a strange quirk is that you can put a space between the -u and the root, but not between the -p and the Cloudera. Usually you'd put in a -P and then it prompts you for your password on here. For this demo, I don't worry too much about you knowing the password on that, so we'll just go right into MySQL Server since this is the standard password for this quick start. And you can see we're now into MySQL. And we're going to do just a couple of quick commands in here. There's show databases, and you follow by the semicolon. That's standard in most of these shell commands, so it knows it's the end of your shell command. And you'll see in here in the Quick Start, Cloudera Quick Start, the MySQL comes with a standard set of databases. These are just, some of these have to do like with the Uzi, which is the Uzi part of Hadoop, where others of these, like customers and employees and stuff like that, those are just for demo purposes. They come as a standard setup in there so that people going in for the first time have a database to play with, which is really good for us, so we don't have to recreate those databases. And you will see on the list here we have a retail_db. And then we can simply do use retail_db. This will set that as a default in MySQL. And then we want to go ahead and show the tables. And if we show the tables, you can see under the database, the retail DB database, we have categories, customers, departments, order items, orders, products. So there's a number of tables in here. And we're going to go ahead and just use a standard SQL command. And if you did our Hive language, you'll note, remember it's the same for HQL also on this. We're just going to select star everything from departments. So there's our departments table, and we're going to list everything on the departments table. And you'll see we have about 6 lines in here, and it has a department ID and a department name. 2 for fitness, 3 for footwear, so on and so forth. Now at this point, I can just go ahead and exit, but it's kind of nice to have this data up here so we can look at it and flip back and forth between the screens. So I'm going to open up another terminal window, and we'll go ahead and zoom in on this also. And it isn't too important for this particular setup, but it's always kind of fun to know what your setup you're working with. What is your host name? And so we'll go ahead and just type that in. This is a Linux command, and it's hostname -f, and you see we're on Quick Start Cloudera. No surprise there. Now this next command is going to be a little bit longer because we're going to be doing our first Sqoop command. And I want to do 2 of them. We're going to list databases and list tables. It's going to take just a moment to get through this because there's a bunch of stuff going on here. So we have Sqoop, we have list databases, we have connect. And under the connect command, we need to let it know how we're connecting. We're going to use the JDBC. This is a very standard one, JDBC MySQL. So you'll see that if you're doing an SQL database, that's how you start it off with. And then the next part, this is where you have to go look it up. It's however it was created. So if your admin created a MySQL server with a certain setup, that's what you have to go by. And you'll see that usually they list this as localhost. So you'll see something like localhost sometimes. There's a lot of different formats, but the most common is either localhost or the actual connection. So in this case, we want to go ahead and do Quick Start 3306. And so Quick Start is the name of the localhost database and how it's hosted on here. And when you set up the Quick Start for Hadoop under Cloudera, it's port 3306 is where that's coming in. So that's where all that's coming from. And so there's our path for that. And then we have to put in our password. We type password, and if you look it up, password on the Cloudera Quick Start is Cloudera. And we have to also let it know the username. And again, if you're doing this, you'd probably put in a minus capital. You can actually just do it for a prompt for the password. So if you leave that out, it'll prompt you. But for this, doesn't really matter. I don't care if you see my password. It's the default one for Cloudera Quick Start. And then the username on here is simply root. And then we're going to put our semicolon at the end. And so we have here our full setup, and we go ahead and list the databases. And you'll see you might get some warnings on here. I haven't run the updates on the Quick Start. I suggest you're not running the updates either if you're doing this for the first time, because it'll do some reformatting on there. And it quickly pops up, and you can see here's all of our the tables we went in there. And if we go back to on the previous window, we should see that these tables match. So here we come in, and here we have our databases, and you can see back up here where we had the CM, customers, employees, and so on. So the databases match. And then we want to go ahead and list the tables for a specific database. So let's go ahead and do that. I'm a very lazy typist, so I'll put the up arrow in. And you can see here, Sqoop list databases. We're just going to go back and change this from databases to list tables. So we want to list the tables in here. Same connection. So most of the connection is the same, except we need to know which tables we're listing. An interesting fact is you can create a table without being under a database. So if you left this blank, it will show the open tables that aren't connected directly to a database or under a database. But what we want to do is right past this last slash on the 3306, we want to put that retail_db. because that's the database we're going to be working with. And this will go in there and show the tables listed under that database. And here we go. We got categories, customers, departments, order items, and products. If we flip back here real quick, there it is, the same thing we had. We had categories, customers, departments, order items, and so on. And so let's go ahead and run our first import command. And again, I'm that lazy typer, so we're going to do Sqoop, and instead of list tables, we want to go ahead and import. So there's our import command. And so once we have our import command in there, then we need to tell it exactly what we're going to import. So everything else is the same. We're importing from the retail DB, so we keep that. And then at the very end, we're going to tag on -- table. That tells it, so we can tell it what table we're importing from. And we're going to import departments. There we go. So this is pretty straightforward, because what's nice about this is you can see the commands are the same. I got the same connection. I change it for whatever database I'm in. Then I come in here, our password and the username are going to be the same. That's all under the MySQL Server setup. And then we let it know what table we're entering in. We run this, and this is going to actually go through the mapper process in Hadoop. So this is a mapping process. It takes the data and it maps it up to different parts in the setup in Hadoop on there, and then saves that data into the Hadoop file system. And it does take it a moment to zip through, which I kind of skipped over for you, since it is running it's designed to run across a cluster, not on a single node. So when you're running on a single node, it's going to run slow, even if you dedicate a couple cores to it. I think I put dedicated 4 cores to this one. And so you can see right down here, we get to the end. It's now mapped in that information, and then we can go in here, we can go under, can flip back to our Hue, and under Hue, on the top, there's databases, and the second icon over is your Hadoop file system. And we can go in here and look at the Hadoop file system, and you'll see it show up underneath our documents. There it is, departments, Cloudera departments. And you can see there's always a delay when I'm working in Hue, which I don't like. And that's the quick start issue. That's not necessarily running it on a server. When I'm running it on a server, you pretty much have to run through some kind of server interface. I still prefer the terminal window. It still runs a lot quicker. But we'll flip back on over here to the command line, and we can do the Hadoop, type in the Hadoop FS, and then list -ls. And if we run this, you'll see underneath our Hadoop file system, there is our departments, which has been added in. And we can also do Hadoop FS, and this is kind of interesting. For those who've gone through the Hadoop file system, everything, you'll recognize this on here. But I'm going to list the contents of departments, and you'll see underneath departments we have part M 000, 001, 002, 003. And so this is interesting because this is how Hadoop saves these files, and this is in the file system. This is not in Hive. So we didn't directly import this into Hive. We put this in the Hadoop file system. Depending on what you're doing, you would then write the schema for Hive to look at the Hadoop file system. Certainly visit our Hive tutorial for more information on Hive specific. So you can see in here are different files that it forms that are part of departments. And we can do something like this. We can look at the contents of one of these files, fs -ls, or a number of the files. And we'll simply do the full path, which is user Cloudera. And then we already know the next one is departments. And then after departments, we're going to put /part star. So this is going to say anything that has part in it. So we have part -m, 000, and so on. We can go ahead and use that cat command or that list command to bring those up. And then we can use the cat command to actually display the contents. And that's a Linux command, Hadoop Linux command, to catenate. Not to be confused with catatonic, catastrophic. There's a lot of cat got your tongue. And we see here fitness, footwear, apparel. That should look really familiar because that's what we had in our MySQL Server. When we went in here, we did a select all on here. There it is, fitness, footwear, apparel, golf, outdoors, and fan shop. And then, of course, it's really important, let's flip back on over here, to be able to tell it where to put the data. So we go back to our import command. So here's our Sqoop Import. We have our connect. We have the DB underneath our connection, our MySQL Server. We have our password, our username, the table where it's going to. The table where it's coming from. And then we can add a target on here. We can put in target directory, and you do have to put the full path. That's a Hadoop thing. It's a good practice to be in. And we're going to add it to department, we'll just do department 1. And so here we now add a target directory in here and user Cloudera department 1. And this will take just a moment before, so I'll go ahead and skip over the process since it's going to run very slowly. It's only running on, like I said, a couple cores, and it's also on a single node. And now we can do the Hadoop. Let's just do the up arrow. File system list. We want just straight list. And when we do the Hadoop file system -ls or list, you'll see that we now have department 1. And we can of course do list department 1. And you can see we have the files inside department 1, and they mirrored what we saw before with the same files in there, in the part MMO00 and so on. If we want to look at them, it'd be the same thing we did before with the cat, except instead of departments, we'd be department 1. There we go. And then that's going to come up with the same data we had before. Now, one of the important things when you're importing data, and it's always a question to ask, is do you filter the data before it comes in? Do we want to filter this data as it comes in so we're not storing everything in our file system? You would think Hadoop, big data, put it all in there. I know from experience that putting it all in there can turn a couple hundred terabytes into a petabyte very rapidly. And suddenly you're having to really add on to that data store, and you're storing duplicate data sometimes. So you really need to be able to filter your data out. And so let's go ahead and use our up arrow to go to our last import, since it's still a lot the same stuff. So we have all of our commands under import. We have the target. We're going to change this to department 2. So we're going to create a new directory for this one. And then after departments, there's another command that we didn't really slide in here, and that's our mapping. And I'll show you what this looks like in a minute. But we're going to put M3 in there. That does have nothing to do with the filtering. I'll show you that in a second, though, what that's for. And we just want to put in where. So where, and what is the where? In this case, we want to know where department ID, and if you want to know where that came from, we can flip back on over here. We have department_IDs. This is where that's coming from. That's just the name of the column on here. And so we come in here to department ID is greater than 4. Simple logic there. You can see where you'd use that for maybe creating buckets for ages, age from 10 to 15, 20 to 30. You might be looking for, there's all kinds of reasons why you could use the where command on here and filter information out. Maybe you're doing word counting and you want to know words that are used less than 100 times. You want to get rid of the and is and all the stuff that's used over and over again. So we'll go ahead and put the where, and then department ID is greater than 4. We'll go ahead and hit enter on here, and this will create our department 2 setup on this. And I'll go ahead and skip over some of the runtime. Again, it runs really slow on a single node. Real quick page through our commands. Let's see, here we go. Our list, and we should see underneath the list the department 2 on here now, and there it is, department 2. And then I can go ahead and do list department 2. You'll see the contents in here, and you'll see that there is only 3 maps, and it could be that the data created 3 maps, but remember I set it up to only do 3 mappers. So there's 0, 1, and 2, and we can go ahead and do a cat on there. Remember, this is department 2, so we want to look at all the contents of these 3 different files, and there it is. It's greater than 4. So we have golf is 5, outdoor 6, fan shop is 7. So we've effectively filtered out our data and just storing the data we want on our file system. So if you're going to store data on here, the next stage is to export the data. Remember, a lot of times you have MySQL Server, and we're continually dumping that data into our long-term storage and access, the Hadoop file system. But what happens when you need to pull that data out and restore a database? Or maybe you have you just merged with a new company. A favorite topic, merging companies and merging databases. That's listed under Nightmare, and how many different names for company can you have? So you can see where being able to export is also equally important, and let's go ahead and do that. And I'm going to flip back over to MySQL Server here, and we'll need to go ahead and create our database we're going to export into. Now, I'm not going to go too much in detail on this command. We're simply creating a table, and the table is going to have, it's pretty much the same table we already have in here from departments. But in this case, we're going to create a table called DEPT. So it's the same setup, but it's just going to, we're just giving it a different name, a different schema. And so we've done that, and we'll go ahead and do a select star from DEPT. There we go. And it's empty. That's what we expect. A new database, a new data table, and it's empty in there. So now we need to go ahead and export our data that we just filtered out into there. So let's flip back on over here to our Sqoop setup, which is just our Linux terminal window. And let's go back up to one of our commands. Here's Sqoop Import. In this case, instead of import, we're going to take the Sqoop and we're going to export. So we're going to just change that, export. And the connection is going to remain the same. So same connect, same database. We're still doing the retail DB. We have the same password, so none of that changes. The big change here is going to be the table. Instead of departments, remember we changed it and gave it a new name. And so we want to change it here also, DEPT. So department. We're not going to worry about the mapper count. And the where was part of our import. There we go. And then finally, it needs to know where to export from. So instead of target directory, we have an export directory. That's where it's coming from. Still user, Cloudera, and we'll keep it as department 2, just so you can see how that data is coming back with that we filtered in. And let's go ahead and run this. It'll take it just a moment to go through its steps. And again, because it's slow, I'm just going to go ahead and skip this so you don't have to sit through it. And once we've wrapped up our export, we'll flip back on over here to MySQL. Use the up arrow, and this time we're going to select star from department, and we can see that there it is. It exported the golf, outdoors, and fan shop. And you can imagine also that you might have to use the where command in your export also. So there's a lot of mixing. The command line for Sqoop is pretty straightforward. You're changing the different variables in there, whether you're creating a table, listing databases. Very powerful tool for bringing your data into the Hadoop file system and exporting it. Now, Flume is a distributed service for collecting, aggregating, and moving large amounts of log data. So kind of focused a little bit on a slightly different set of data, although you'll find these overlap a lot. You can certainly use Flume to do a lot of things that you can do in Sqoop and vice versa. Flume ingests the data, so we're looking at, like, say, a JSON call to a website. XML documents, unstructured and semi-structured data is most commonly digested by Flume. Best example I saw was a Twitter account pulling Twitter feeds into a Hadoop system. So it ingests online streaming data from social media, Twitter, log files, so we want to know what's going on with error codes on your servers and all those log files, web server, what's going on in your web server. We can bring all this stuff in and just dump it into the Hadoop data file system to be looked at and processed later. And it's a web server, cloud, social media data. Again, all those different sources it can be. It's kind of endless. It just depends on what your company needs. Versatility of Hadoop is what makes it such a powerful source to add into a company. And so it comes in there, you have your source, it goes through the channels, it then goes through kind of a sync feature to make sure everything is in sync, and then it dumps it into the Hadoop file system. So we've covered in the Hadoop file system the first two things. Let's look at some of the scripting languages they have. And so we have the two here, and you can also think of these, it actually says scripting and SQL queries. A lot of times they're both referred to as queries. So you have both the Pig and the Hive. And Pig is used to analyze data in Hadoop. It provides a high-level data processing language to perform numerous operations on the data. And it's made out of Pig Latin, language for scripting. Pig Latin compiler converts Pig Latin code to execute code. And then you have your ETL. The ETL provides a platform for building data flow for ETL. And ETL is like the catch 3 letters now on any job interview I look at. It says ETL. It just means extract, transfer, and load. So all we're doing is extracting the data, transferring it to where we need it, and then loading it into, in this case, a Hadoop file system. And there's other pieces to that. It's actually a big thing because whenever you're extracting data, do you want to dump all the data or do you want to do some kind of pre-processing so you're only bringing in what you want? And then one of the cool things about Pig Latin is 10 lines of Pig Latin script is around 200 lines of MapReduce job. Again, the MapReduce is the back-end processes that go on. So if we have Pig, and I'll be honest with you, Pig is very easy to use, but as a scripter programmer, I find it's more for people who just need a quick pull of the data and able to do some very basic things very easily. So if you're doing some very high-end processing and model building, you usually end up in something else. So Pig's great for that. Like if you're in the management, you need to build a quick query report, Pig is really good for that. And so it definitely has its place. It's definitely a very useful script to know. And the pig Latin scripts, they call it the grunt shell. I guess it goes with pig because they grunt. You have your pig server. You have a parser, an optimizer, a compiler, an execution engine. And that's all part of the Apache pig. And this then goes into the MapReduce, which then goes into the Hadoop file system in the Hadoop. And you'll see Apache with a lot of these because it's under the open source. Hadoop's under the Apache open source. So all this stuff is you'll see under Apache with the name tag on there. So enough theory, let's dive in and show you a quick demo on some of the commands you can do in pig. Today's setup will continue as we have in the last 3 demos to go ahead and use Cloudera Quick Start. And we'll be doing this in VirtualBox. We do have a tutorial in setting that up. You can send a note to our Simplilearn team and then get that link to you. Once your Cloudera Quick Start has spun up, and remember this is VirtualBox. We've created a virtual machine, and this virtual machine is CentOS Linux. Once it's spun up, you'll be in a full Linux system here. And as you can see, we have Thunderbird browser, which opens up to the Hadoop basic system browser. And we can go underneath the hue, where it comes up by default. If you click on the pull-down menu and go under editor, you can see there's our Impala, our Hive, pig, along with a bunch of other query languages you can use. And we're going under pig. And then once you're in pig, we can go ahead and use our command line here and just click that little blue button to start it up and running. We will actually be working in terminal window. And so if you're in the Cloudera Quick Start, you can open up the terminal window up top, or if you're in your own setup and you're logged in, you can easily use all of your commands here in terminal window. And we'll zoom in. That way you get a nice view of what's going on. There we go. Now for our first command, we're going to go ahead and do a Hadoop command and import some data into the Hadoop system, in this case a pig input. And let's just take a look at this. We have Hadoop. Now let's know it's going to be a Hadoop command. DFS. There's actually 4 variations of DFS. So if you have HDFS or whatever, that's fine. All 4 of them used to be different setups underneath different things, and now they all do the same thing. And we want to put this file, which in this case is under Home Cloudera Documents and Sample, and we just want to take that and put it into the pig input. And let's take a look at that file. If I go under my document browsers and open this up, you'll see it's got a simple ID, name, profession, and age. We have one Jack Engineer 25, and that was in one of our earlier things we had in there. And so let's go ahead and hit enter and execute this, and now we've uploaded that data and it's gone into our pig input. And then a lot of the Hadoop commands mimic the Linux commands, and so you'll see we have cat as one of our commands, or it has a hyphen before it. So we execute that with Hadoop DFS -cat /pig input, because that's what we called it. That's where we put our sample CSV at. And we execute this. You can see from our Hadoop system, it's going to go in and pull that up, and sure enough, it pulls out the data file we just put in there. And then we can simply enter the pig Latin or pig editor mode by typing in pig. And we can see here by our grunt, I told you that's how it was going to tell you were in pig Latin. There's our grunt command line. So we are now in the pig shell. And then we'll go ahead and put our load command in here. And the way this works is I'm going to have office equals load. And here's my load. In this case, it's going to be pig input. We have that in single brackets. You remember that's where the data is in the Hadoop file system where we dumped it into there. We're going to be using pig storage. Our data was separated as with a comma. So there's our comma separator. And then we have as. And in this case, we have an ID, character array, name, character array, profession, character array, and age, character array. And we're just going to do them all as character arrays just to keep this simple for this one. And then when I hit put this all in here, you can see that's our full command line going in, and we have our semicolon at the end. So when I hit enter, it's now set office up. But it hasn't actually done anything yet. It doesn't do anything until we do dump office. So there's our command to execute whatever we've loaded or whatever setup we have in here. And we run that, you can see it go through the different languages, and this is going through the MapReduce. Remember, we're not doing this locally, we're doing this on the Hadoop setup. And once we finished our dump, you can see we have ID, name, profession, age, and all the information that we just dumped into our pig. we can now do, let's say we have a request just for, we'll keep it simple in here, but just for the name and age. And so we can go office, we'll call it each as our variable, underscore each, and we'll say for each office, generate name, comma, age. And for each means that we're going to do this for each row. And if you're thinking MapReduce, you know that this is a map function because it's mapping each row and generating name and age on here. And of course, we want to go ahead and close it with a semicolon. And then once we've created our query or the command line in here, let's go ahead and dump office underscore each in with our semicolon. And this will go through our MapReduce setup on here. And if we were on a large cluster, the same processing time would happen. In fact, it's really slow because I have multiple things on this computer, and this particular virtual box is only using a quarter of my processor. It's only dedicated to this. And you can see here, there it is, name and age. And it also included the top row since we didn't delete that out of there or tell it not to. And that's fine for this example, but you need to be aware of those things when you're processing a significantly large amount of data or any data. And we can also do office, and we'll call this DSC for descending. So maybe the boss comes to you and says, hey, can we order office by ID descending? And of course your boss, you've taught him how to, your shareholder, it sounds a little derogatory when I say boss. You've talked to the shareholder and you said, and you've taught them a little bit of Pig Latin, and they know that they can now create office description, and we can order office by ID description. And of course, once we do that, we have to dump office underscore description so that it'll actually execute, and there goes into our MapReduce. It'll take just a moment for it to come up because again I'm running on only a quarter of my processor, and you can see we now have our IDs in descending order returned. Let's also look at, and this is so important with anytime you're dealing with big data, let's create office with a limit. And you could of course do any of this instead of with office, we could do this with office descending, so you get just the top 2 IDs on there. But we're going to limit just to 2, and of course to execute that we have to dump office underscore limit. And you can just think of dumping your garbage into the pig pen for the pig to eat. There we go, dump office limit 2, and that's going to just limit our office to the top 2. And for our output, we get our first row, which had our ID, name, profession, and age, and our second row, which is Jack, who's an engineer. And let's do a filter. We'll call it office underscore filter. You guessed it, equals filter office by profession equals. And keep note, this is similar to how Python does it with the double equal signs for equal for doing a true-false statement. So for your logic statement, remember to use 2 equal signs in pig. And we're going to say it equals doctor. So we want to find out how many doctors do we have on our list. And we'll go ahead and do our dump. We're dumping all our garbage into the pig pen, and we're letting pig take over and see what it can find out and see who's a doctor on our list. And we find employee ID number 2, Bob, is a doctor, 30 years old. For this next section, we're going to cover something we see a lot nowadays in data analysis, and that's word counting, tokenization. That is one of the next big steps as we move forward in our data analysis, where we go from, say, stock market analysis of highs and lows and all the numbers to what are people saying about companies on Twitter? What are they saying on the web pages and on Facebook? Suddenly you need to start counting words and finding out how many words are total, how many are in the first part of the document, and so on. We're going to cover a very basic word count example. And in this case, I've created a document called wordrows.txt. And you can see here we have Simplilearn is a company supporting online learning. Simplilearn helps people attain their certifications. Simplilearn is an online community. I love Simplilearn. I love programming. I love data analysis. And I went and saved this into my documents folder so we could use it. And let me go ahead and open up a new terminal window for our word count. Let me go ahead and close the old one. So we're going to go in here, and instead of doing this as pig, we're going to do pig -x local. And what I'm doing is I'm telling the pig to start the pig shell, but we're going to be looking at files local to our virtual box or this CentOS machine. And let me go ahead and hit enter on there. Just maximize this up. There we go. And it'll load pig up, and it's going to look just the same as the pig we were doing, which was defaulted to our Hadoop system, to our HDFS. This is now defaulted to the local system. And now we're going to create lines, and we're going to load it straight from the file. Remember last time we took the HDFS and loaded it into there, and then loaded it into pig. Since we're on the local, we're just going to run a local script. We have lines equals load home, the actual full path, home, Cloudera, documents, and I called it wordrows.text. And as line is a character array, so each line, and you can change this to read each document. I certainly have done a lot of document analysis, and then you go through and do word counts and different kind of counts in there. So once we go ahead and create our line, instead of doing the dump, we're going to go ahead and start entering all of our different setups for each of our steps we want to go through. And let's just take a look at this next one, because the load is straightforward. We're loading from this particular file. Since we're locals, loading it directly from here instead of going into the Hadoop file system. And it says as, and then each line is read as a character array. Now we're going to do words equal for each of the lines, generate flat tokenize line space as word. Now there's a lot of ways to do this. This is if you're a programmer, you're just splitting the line up by spaces. There's actual ways to tokenize it. You gotta look for periods, capitalization. There's all kinds of other things you play with this. But for the most basic word count, we're just going to separate it by spaces. The flatten takes the line and just creates it flattens each of the words out. So this is, we're just going to generate a bunch of words for each line. And then each of those words is as a word. A little confusing in there, but if you really think about it, we're just going down each line, separating it out, and we're generating a list of words. One thing to note is the default for tokenize. You can just do tokenize line without the space in there. If you do that, it'll automatically tokenize it by space. You can do either one. And then we're going to do group. We're going to group it by words. So we're going to group words by word. So when we split it up, each token is a word and it's a list of words. And so we're going to grouped equals group words by word. So we're going to group all the same words together. And if we're going to group them, then we want to go ahead and count them. And so for count, we'll go ahead and create a word count variable. And here's our for each. So for each grouped is our line where we group all the words in the line that are similar. We're going to generate a group. And then we're going to count the words. For each grouped, so for each line where we group the words together, we're going to generate a group, and that's going to count the words. So we want to know the word count in each of those. And that comes back in our word count. And finally, we want to take this and we want to go ahead and dump word count. And this is a little bit more what you see when you start looking at grunt scripts. You'll see right here, these lines right here, we have each of the steps you take to get there. So we load our file. For each of our lines, we're going to generate and tokenize it into words. Then we're going to take the words and we're going to group them by same words. For each grouped, we're going to generate a group and we're just going to count the words. So we're going to summarize all the words in here. And let's go ahead and do our dump word count, which executes all this. And it goes through our MapReduce. It's actually a local runner. You'll see down here, you start seeing where they still have MapReduce, but it's a special runner. We're mapping it. That's a part of each row being counted and grouped. And then when we do the word count, that's the reducer. The reducer creates these keys. And you can see I is used 3 times, A came up once, and came up once, is 2. You can continue on down here to attain, online, people, company, analysis. Simplilearn, they took the top rating with 4. Certification. So all these things are then counted in the how many words are used. And in data analysis, this is probably the beginnings of data analysis, where you might look at it and say, oh, they mentioned love 3 times. So whatever's going on in this post, it's about love. And what do they love? And then you might attach that to the different objects in here. So you can see that Pig Latin is fairly easy to use. There's nothing really, it takes a little bit to learn the script. Depending on how good your memory is. As I get older, my memory leaks a little bit more, so I don't memorize it as much. But that was pretty straightforward, the script we put in there. And then it goes through the full MapReduce localized run, comes out, and like I said, it's very easy to use. That's why people like Pig Latin, is because it's intuitive. One of the things I like about Pig Latin is when I'm troubleshooting. When we're troubleshooting, a lot of times you're working with a small amount of data, and you start doing one line at a time, and so I can go So lines equal load, and there's my loaded text, and maybe I'll just dump lines. And then it's going to run, it's going to show me all the lines that I'm working on in this small amount of data. And that way I can test that. If I got an error on there that said, oh, this isn't working, maybe I'll be like, oh my gosh, I'm in MapReduce, or I'm in the basic grunt shell instead of the local path grunt. So maybe it'll generate an error on there. And you can see here it just shows each of the lines going down. And if you're going to know Pig, Hive is the other one that's really popular for easy query. Hive facilitates reading, writing, and managing large data sets residing in the distributed storage using SQL, Hive query language. And this is important because a lot of times you're coming from an SQL server. There's your enterprise set up, and now you're archiving a history of what's going on that server. So you're continually pulling data using Sqoop onto your into your HBase, Hive database. And as it comes in there, it'd be nice to just use that same query to pull the data out of the Hadoop file system. And that's exactly what it does. So you have Hive command line. You can also use a JBC or ODBC driver. And those drivers, like if you're working in Java or you're working in Python, you can use those drivers to access Hive. So you don't have to go through the Hive command line. But it makes it real quick. I can take a Hive command line and just punch in a couple words and pull up my data. And so it provides user-defined functions, UDF, for data mining, document indexing, log processing, again, anything that is in some kind of SQL format. If it's stored that properly on the Hadoop file system, you can use your Hive to pull it out. And you see even a more robust image of what's in the Hive. There's your client machine, that's you on your laptop or you're logged in wherever you're at, writing your script. That goes into the driver where you have your compiler, your optimizer, executor. You also have your JDBC, ODBC connections, which goes into the Hive Thrift server, which then goes into the driver. Your Hive web interface, so you can just log in on the web and start typing away your SQL commands, and that again goes to the driver, and all those pieces. And those pieces go to your job tracker, your name node, and your actual Hadoop file system. So with all that, let's take a look at a demo on HiveQL or HQL. Before I dive into the hands-on demo, let's take a look at the website, hive.apache.org. That's the main website since Apache, it's an Apache open source software. This is the main software or the main site for the build. And if you go in here, you'll see that they're slowly migrating Hive into Beehive. And so if you see Beehive versus Hive, note the Beehive is a new release is coming out. That's all it is, and it reflects a lot of the same functionality of Hive. It's the same thing. And then we like to pull up some kind of documentation on commands. And for this, I'm actually going to go to Hortonworks Hive cheat sheet. And that's because Hortonworks and Cloudera are two of the most common used builds for Hadoop and for which include Hive and all the different tools in there. And so Hortonworks has a pretty good PDF you can download cheat sheet on there. I believe Cloudera does too, but we'll go ahead and just look at the Horton one, because it's the one that comes up really good. And you can see when we look at the query language, it compares MySQL Server to HiveQL or HQL. And you can see the basic select. We select from columns, from table where conditions exist. You know, most basic command on there. And they have different things you can do with it, just like you do with your SQL. And if you scroll down, you'll see data types. So here's your integer, your float, your binary, double string, timestamp, and all the different data types you can use. Some different semantics, different keys, features, functions for running a Hive query, command line setup, and of course the Hive shell setup in here. So you can see right here, if we loop through it, it has a lot of your basic stuff. And we're basically looking at SQL across a Horton database. We're going to go ahead and run our Hadoop cluster Hive demo. And I'm going to go ahead and use the Cloudera Quick Start. And this is in the virtual box. So again, we have an Oracle virtual box, which is open source. And then we have our Cloudera Quick Start, which is the Hadoop setup on a single node. Now, obviously, Hadoop and Hive are designed to run across a cluster of computers. So when we talk about a single node, it's for education, testing, that kind of thing. And if you have a chance, you can always go back and look at our demo we had on setting up a Hadoop system in a single cluster. Just set a note down below in the YouTube video, and our team will get in contact with you and send you that link if you don't already have it. Or you can contact us at the www.simplilearn.com. Now in here, it's always important to note that you do need on your computer. If you're running on Windows, because I'm on a Windows machine, you're going to need probably about 12 gigabytes to actually run this. It used to be you could buy with a lot less, but as things have evolved, they take up more and more resources. And you need the professional version. If you have the home version, I was able to get that to run, but boy, did it take a lot of extra work to get the home version to let me use the virtual setup on there. And we'll simply click on the Cloudera Quick Start, and I'm going to go and just start that up. And this is starting up our Linux. So we have our Windows 10, which is the computer I'm on, and then I have the virtual box, which is going to have a Linux operating system in it. And we'll skip ahead so you don't have to watch the whole install. Something interesting to know about the Cloudera is that it's running on Linux CentOS, and for whatever reason, I've always had to click on it and hit the escape button for it to spin up. And then you'll see the DOS come in here. Now that our Cloudera is spun up on our virtual machine with the Linux on, we can see here we have our, it uses the Thunderbird browser on here by default and automatically opens up a number of different tabs for us. And a quick note, because I mentioned like the restrictions on getting set up on your own computer. If you have a home edition computer and you're worried about setting it up on there, you can also go in there and spin up a 1-month free service on Amazon Web Service to play with this. So there's other options. You're not stuck with just doing it on the quick start menu. You can spin this up in many other ways. Now the first thing we want to note is that we've come in here into Cloudera, and I'm going to access this in 2 ways. The first one is we're going to use Hue. And I'm going to open up Hue, and it'll take it a moment to load from the setup on here. And Hue is nice. If I go in and use Hue as an editor into Hive or into the Hadoop setup, usually I'm doing it as a from an admin side because it has a lot more information, a lot of visuals, less to do with actually diving in there and just executing code. And you can also write this code into files and scripts, and there's other ways you can upload it into Hive. But today we're going to look at the command lines, and we'll upload it into Hue, and then we'll go into and actually do our work in a terminal window under the Hive shell. Now in the Hue browser window, if you go under Query and click on the pull down menu, and then you go under Editor, and you'll see Hive. There we go. There's our Hive setup. I go and click on Hive, and this will open up our query down here, and now it has a nice little B that shows our Hive going, and we can go something very simple down here like show databases, and we follow it with the semicolon. And that's the standard in Hive, is you always add our punctuation at the end there. And I'll go ahead and run this, and the query will show up underneath. And you'll see down here, since this is a new quick start I just put on here, you'll see it has the default down here for the databases. That's the database name. I haven't actually created any databases on here. And then there's a lot of other like assistant function, tables, your databases up here. There's all kinds of things you can research, you can look at through Hue as far as a bigger picture. The downside of this is it always seems to lag. For me, whenever I'm doing this, I always seem to run slow. So if you're in Cloudera, you can open up a terminal window. They actually have an icon at the top. You can also go under Applications, and under Applications, System Tools, and Terminal. Either one will work. It's just a regular terminal window. And this terminal window is now running underneath our Linux. So this is a Linux terminal window, or on our virtual machine, which is resting on our regular Windows 10 machine. And we'll go ahead and zoom this in so you can see the text better on your own video. And I simply just clicked on View and Zoom in. And then all we have to do is type in Hive. And this will open up the shell on here. And it takes it just a moment to load. When starting up Hive, I also want to note that depending on your rights on the computer you're on in your action, you might have to do sudo Hive and put in your password and username. Most computers are usually set up with the Hive login. Again, it just depends on how you're accessing the Linux system and the Hive shell. Once we're in here, we can go ahead and do a simple HQL command, show databases. And if we do that, we'll see here that we don't have any databases. So we can go ahead and create a database, and we'll just call it Office for today, for this moment. Now if I do show, we'll just do the up arrow. Up arrow is a hotkey that works in both Linux and in Hive. So I can go back and paste through all the commands I've typed in. And we can see now that I have my, there's of course the default database, and then there's the Office database. So now we've created a database. It's pretty quick and easy. And we can go ahead and drop the database. We can do drop database Office. Now this will work on this database because it's empty. If your database was not empty, you would have to do cascade. And that drops all the tables in the database and the database itself. Now if we do show database, And we'll go ahead and recreate our database because we're going to use the Office database for the rest of this hands-on demo. A really handy command to now set with the SQL or HQL is to use Office. And what that does is that sets Office as the default database. So instead of having to reference the database every time we work with a table, it now automatically assumes that's the database being used, whatever tables we're working on. The difference is you put the database name period table, and I'll show you in just a minute what that looks like and how that's different. If we're going to have a table and a database, we should probably load some data into it. So let me go ahead and switch gears here and open up a terminal window. You can just open another terminal window and it'll open up right on top of the one that you have Hive shell running in. And when we're in this terminal window, first we're going to go ahead and just do a list, which is of course a Linux command. You can see all the files I have in here. This is the default load. We can change directory to documents. We can list in documents, and we're actually going to be looking at employee.csv. A Linux command is the cat. You can use this actually to combine documents. There's all kinds of things that cat does, but if we want to just display the contents of our employee.csv file, we can simply do cat employee CSV. And when we're looking at this, we want to know a couple things. One, there's a line at the top. Okay, so the very first thing we notice is that we have a header line. The next thing we notice is that the data is comma separated. And in this particular case, you'll see a space here. Generally, with these, you got to be real careful with spaces. There's all kinds of things you got to watch out for because they can cause issues. These spaces won't, because these are all strings that the space is connected to. If this was a space next to the integer, you would get a null value that comes into the database without doing something extra in there. Now, with most of Hadoop, that's important to know that you're writing the data once, reading it many times, and that's true of almost all your Hadoop things coming in. So you really want to process the data before it gets into the database. And for those of you who have studied data transformation, that's the ETL, where you extract, transfer, form, and then load the data. So you really want to extract and transform before putting it into the Hive. Then you load it into the Hive with the transformed data. And of course, we also want to note the schema. We have an integer, string, string, integer, integer. So we kept it pretty simple in here as far as the way the data is set up. The last thing that you're going to want to look up is the source. Since we're doing local uploads, we want to know what the path is. We have the whole path. In this case, it's home/Cloudera/documents. And these are just text documents we're working with right now. We're not doing anything fancy. So we can do a simple get edit employee.csv, and you'll see it comes up here. It's just a text document, so I can easily remove these added spaces. There we go. And then we go ahead and just save it. And so now it has the new setup in there. We've edited it. The gedit is usually one of the default that loads into Linux. So any text editor will do. Back to the Hive shell. So let's go ahead and create a table employee. And what I want you to note here is I did not put the semicolon on the end here. The semicolon tells it to execute that line. So this is kind of nice if you can actually just paste it in if you have it written on another sheet. And you can see right here where I have create table employee, and it goes into the next line on there so I can do all of my commands at once. Now, just so I don't have any typo errors, I went ahead and just pasted the next 3 lines in. And the next one is our schema. If you remember correctly from the other side, we had the different values in here, which was ID, name, department, year of joining, and salary. And the ID is an integer, name is a string, department string, year of joining, integer, salary, an integer. And they're in brackets. We put closed brackets around them. And you could do this all as one line. And then we have row format delimited fields terminated by comma. And this is important because the default is tabs. So if I do it now, it won't find any terminated fields. So you'll get a bunch of null values loaded into your table. And then finally, our table properties, we want to skip the header line count equals 1. Now, this is a lot of work for uploading a single file. It's kind of goofy when you're uploading a single file that you have to put all this in here. But keep in mind, Hive and Hadoop is designed for writing many files into the database. You write them all in there, and then they're saved. It's an archive. It's a data warehouse. And then you're able to do all your queries on them. So a lot of times we're not looking at just the one file coming up. We're loading hundreds of files. You have your reports coming off of your main database. All those reports are being loaded. You have your log files. You have, all this different data is being dumped into Hadoop, and in this case Hive on top of Hadoop. And so we need to let it know, hey, how do I handle these files coming in? And then we have the semicolon at the end, which lets us know to go ahead and run this line. And so we'll go ahead and run that. And now if we do a show tables, you can see there's our employee on there. We can also describe. If we do describe employee, you can see that we have our ID integer, name string, department string, year of joining integer, and salary integer. And then finally, let's just do a select star from employee, very basic SQL and HQL command, selecting data. And it's going to come up and we haven't put anything in it, so as we expect, there's no data in it. So if we flip back to our Linux terminal window, you can see where we did the cat employee.csv, and you can see all the data we expect to come into it. And we also did our pwd, and right here you see the path. You need that full path when you are loading data. You can do a browse, and if I did it right now with just the employee.csv as a name, it will work. But that is a really bad habit. In general, when you're loading data, because it's you don't know what else is going on in the computer, you want to do the full path almost in all your data loads. So let's go ahead and flip back over here to our Hive shell we're working in. And the command for this is load data. So that says, hey, we're loading data. That's a Hive command, HQL. And we want local data, so you got to put down local in path. So now it needs to know where the path is. Now, to make this more legible, I'm just going to go ahead and hit enter, and then we'll just paste the full path in there, which I have stored over on the side, like a good prepared demo. And you'll see here we have home, Cloudera, documents, employee.csv. So it's a whole path for this text document in here. And we go ahead and hit enter in there, and then we have to let it know where the data is going. So now we have a source and we need a destination. And it's going to go into the table, and we'll just call it employee. We'll just match the table in there. And because I want it to execute, we put the semicolon on the end. It goes ahead and executes all three lines. Now if we go back, if you remember we did the select star from employee, just using the up arrow to page through my different commands I've already typed in. You can see right here we have, as we expect, we have Rose, Sam, Mike, and Nick, and we have all their information showing in our 4 rows. And then let's go ahead and do select and count. We'll just look at a couple of these different select options you can do. We're going to count everything from employee. Now this is kind of interesting because the first one just pops up with a basic select, because it doesn't need to go through the full MapReduce phase. But when you start doing a count, it does go through the full MapReduce setup in the Hive and Hadoop. And because I'm doing this demo on a single node Cloudera virtual box on top of a Windows 10, all the benefits of running it on a cluster are gone, and instead it's now going through all those added layers, so it takes longer to run. Like I said, when you do a single node, as I said earlier, it doesn't do any good as an actual distribution because you're only running it on one computer, and then you've added all these different layers to run it. And we see it comes up with 4, and that's what we expect. We have 4 rows. We expect 4 at the end. And if you remember from our cheat sheet, which we brought up here from Horton's, it's a pretty good one, there's all these different commands we can do. We'll look at one more command where we do the what they call subqueries right down here, because that's really common to do a lot of subqueries. And so we'll do select star, or all different columns, from employee. Now if we weren't using the Office database, it would look like this, from office.employee. And either one will work on this particular one because we have Office set as a default on there. So from Office employee, and then the command where creates a subset. And in this case, we want to know where the salary is greater than 25,000. There we go. And of course we end with our semicolon. And if we run this query, you can see it pops up, and there's our salaries, the people, top earners. We have Rose in IT and Mike in HR. Kudos to them. Of course they're fictional. We don't actually have a Rose and a Mike in those positions, or maybe we do. So finally what we want to go ahead and do is we're done with this table. Now remember, you're dealing with a data warehouse, so you usually don't do a lot of dropping of tables and databases. But we're going to go ahead and drop this table here. Before we drop it, one more quick note is we can change it. So what we're going to do is we're going to alter table, office, employee, and we want to go ahead and rename it. There's some other commands you can do in here, but rename's pretty common, and we're going to rename it to, and it's going to stay in office, and it turns out one of our shareholders really doesn't like the word employee. He wants employees plural. It's a big deal to him. So let's go ahead and change that name for the table. It's that easy because it's just changing the metadata on there. And now if we do show tables, you'll see we now have employees, not employee. And then at this point, maybe we're doing some house cleaning because this is all practice. So we're going to go ahead and drop table, and we'll drop table employees because we changed the name in there. So if we did employee, it'd just give us an error. And now if we do show tables, you'll see all the tables are gone. Now the next thing we want to go ahead and take a look at, and we're going to walk back through the loading of data just real quick because we're going to load 2 tables in here. And let me just float back to our terminal window so we can see what those tables are that we're loading. And so up here we have a customer file, and we have an order file. We want to go ahead and put the customers and the orders into here. So those are the 2 we're doing. And of course, it's always nice to see what you're working with. So let's do our cat customer.csv. We could always do gedit, but we don't really need to edit these. We just want to take a look at the data in customer. And important in here is, again, we have a header, so we have to skip a line, comma separated. Nothing odd with the data. We have our schema, which is integer, string, integer, string, integer. So you'd want to take that, note that down, or flip back and forth when you're doing it. And then let's go ahead and do cat order.csv, and we can see we have OID, which I'm guessing is the order ID. We have a date. Oh, something new. We've done integers and strings, but we haven't done date. When you're importing new and you never worked with the date, date's always one of the more trickier fields to port in. And that's true of just about any scripting language I've worked with. All of them have their own idea of how date's supposed to be formatted, what the default is. This particular format, where it's year, and it has all 4 digits, dash month, 2 digits, dash day, is the standard import for the Hive. So you'll have to look up and see what the different formats are if you're going to do a different format in there coming in, or you're not able to pre-process the data. But this would be a pre-processing of the data thing coming in. If you remember correctly from our ETL, which is just in case you weren't able to hear me last time, ETL, which stands for extract, transform, then load. So you want to make sure you're transforming this data before it gets into here. And so we're going to go ahead and bring both this data in here. And really we're doing this so we can show you the basic join. There is, if you remember from our setup, merge, join, all kinds of different things you can do. But joining different data sets is so common. So it's really important to know how to do this. We need to go ahead and bring in these 2 data sets. And you can see where I just created a table customer. Here's our schema, the integer, name, age, address, salary. Here's our delimited by commas, and our table properties where we skip a line. Well, let's go ahead and load the data first, and then we'll do that with our order. And let's go ahead and put that in here, and I've got it split into 3 lines so you can see it easily. We got load data local in path. So we know we're loading data, we know it's local, and we have the path. Here's the complete path for, oops, this is supposed to be order, CSV. Grab the wrong one. Of course, it's going to give me errors because you can't recreate the same table on there. And here we go, create table. Here's our integer, date, customer, the basic setup that we had coming in here for our schema, row format, commas, table properties, skip header line. And then finally, let's load the data into our order table. Load data local in path, home Cloudera documents order.csv into table order. Now if we did everything right, we should be able to do select star from customer. And you can see we have all 7 customers, and then we can do select star from order, and we have 4 orders. So this is just like a quick frame. We have, a lot of times when you have your customer databases in business, you have thousands of customers from years and years, and some of them, they close their business, they change names, all kinds of things happen. So what we want to do is we want to go ahead and find just the information connected to these orders and who's connected to them. And so let's go ahead and do, it's a select, because we're going to display information. So select, and this is kind of interesting. We're going to do c.id, and I'm going to define C as customer, as a customer table in just a minute. Then we're going to do c.name, and again we're going to define the c.age. So this means from the customer we want to know their ID, their name, their age, and then I'd also like to know the order amount. So let's do O for .amount. And then this is where we need to go ahead and define what we're doing. and I'll go ahead and capitalize from customer. So we're going to take the customer table in here, and we're going to name it C. That's where the C comes from. So that's the customer table C, and we want to join order as O. That's where our O comes from. So the O.amount is what we're joining in there. And then we want to do this on, we got to tell it how to connect the two tables. C.id equals O.customer underscore ID. So now we know how they're joined. And now remember, we have 7 customers in here. We have 4 orders. And as it processes, we should get a return of 4 different names joined together. And they're joined based on, of course, the orders on there. And once we're done, we now have the order number, the person who made the order, their age, and the amount of the order, which came from the order table. So you have your different information, and you can see how the join works here. Very common use of tables and HQL and SQL. And let's do one more thing with our database, and then I'll show you a couple other Hive commands. And let's go ahead and do a drop, and we're going to drop database office. And if you're looking at this and you remember from earlier, this will give me an error. And let's just see what that looks like. It says failed to execute, exception, 1 or more tables exist. So if you remember from before, you can't just drop a database unless you tell it to cascade. That lets it know, I don't care how many tables are in it, let's get rid of it. And in Hadoop, since it's it's a warehouse, a data warehouse, you usually don't do a lot of dropping. Maybe at the beginning when you're developing the schemas and you realize you messed up, you might drop some stuff. But down the road, you're really just adding commodity machines to take up so you can store more stuff on it. So you usually don't do a lot of database dropping. And some other fun commands to know is you can do select round 2.3 as round value. You can do a round off in Hive. We can do as floor value, which is going to give us a 2, so it turns it into an integer versus a float. It goes down, basically truncates it, but it goes down. And we can also do ceiling, which is going to round it up. So we're looking for the next integer above. There's a few commands we didn't show in here because we're on a single node. As an admin, to help speediate the process, you usually add in partitions for the data and buckets. You can't do that on a single node because when you add a partition, it partitions it across separate nodes. But beyond that, you can see that it's very straightforward. We have SQL coming in, and all your basic queries that are in SQL are very similar to HQL. So Spark, real-time data analysis. And I told you Spark is its own animal. So we're going to touch very little on Spark as far as how big and robust it is. But we're going to talk a little bit about Spark. Spark is an open source distributed computing engine for processing and analyzing huge volumes of real-time data. So it runs 100 times faster than MapReduce. MapReduce is the basics of the Hadoop system, which is usually set up in a Java code. In Spark, the MapReduce, instead of running what happens in MapReduce is it pulls it into the RAM, writes it to the hard drive, reads it off the hard drive, shuffles it around, writes it back to the hard drive, pulls it off the hard drive, does its processing, and you get the impression it's going in and out of RAM to the hard drive and back up again. So if you don't have a lot of RAM and you have older computers and you don't have the RAM to process something, then Spark and Hadoop are going to run the same speed. Otherwise, Spark goes, hey, let's keep this all in the RAM and run faster. And that's what we're talking about, is provides in-memory computation of data. So it's fast. You can see the guy running through the door there. Speedy versus very slow Hadoop wandering around. It is used to process and analyze real-time streaming data, such as stock market and banking data. So the Spark can have its own stuff going on, and then it can access the Hadoop database. It can pull data just like Sqoop and Flume do. So it has all those features in it. And you can even run Spark with its own yarn outside of Hadoop. There's also Spark on Mesos, which is another resource manager, although yarn is most commonly used. And currently Spark pretty much comes installed with Hadoop. And so your Spark running on top of Hadoop will use the same nodes. It has its own manager, and it utilizes the RAM. So you'll have both. You can have the Spark on top of there. And here we go. You have your driver program, your Spark context. It goes into your cluster manager, your yarn. Then you have your worker nodes, which are going to be executing tasks and cache. And it's important to remember when you're running the Spark setup, even though these are commodity machines, we're still usually, a lot of them are like 128 gigabytes of RAM. so that Spark can run these high-end processes. Certainly if it's not accessed very much and you're building a Hadoop cluster, you could drop that RAM way down if you're doing just queries without any kind of processing on there, and you're not doing a lot of queries. But generally Spark, you're looking at higher end. They're still commodity machines to do your work. And now we get into the Hadoop machine learning. And so machine learning is its own animal. I keep saying that these are all kind of unique things. Mahout is being phased out. I mean, people still use it. It's still important. If you can write your basic machine learning that has most of the tools in there, you certainly can do it in Mahout. Mahout, again, writes to the hard drive, reads from the hard drive. You can do all that in Spark, and it's faster because it's just in RAM. And so Spark has its own machine learning tools in it. And you can also use PySpark, which then accesses all the different Python tools, and there's just so many tools you can dump into Spark. Mahout is very limited, but it's also very basic, which in itself can be really good. Sometimes simple is better. So Mahout is used to create scalable and distributed machine learning algorithms. So here we have our Mahout environment. It builds a machine learning application. So you're doing linear regression, you're doing clustering, you're doing classification models. It has a library that contains inbuilt algorithms for all of these, and then it has collaborative filtering. And again, there's our classification and there's our clustering. Regression, so you have your different machine learning tools. We can easily classify a large amount of data using Mahout. So this brings us to the next set of tools we have, or the next tool, which is the Apache Ambari. Ambari is an open source tool responsible for keeping track of running applications and their statuses. Think of this as like a traffic cop, more like a security guard. You can open it up and see what's going on. And so the Apache Ambari manages, monitors, and provisions Hadoop clusters, provides a central management service to start, stop, and configure Hadoop services. So again, it's like a traffic cop. Hey, stop over there, start, keep going. Hey, what's going on over that area in the through lane on the high-speed freeway? And you can open this up and you have a really easy view of what's going on. And so you can see right here you have the Ambari web. The Ambari web is what you're looking at. That's your interface that you've logged into. The Ambari server, this will be usually on the master node. It's usually, if you're going to install Ambari, you might as well just install it on the same node. And it connects up to the database, and then it has agents, and each agent takes a look and see what's going on with its host server. And if you're going to have two more systems, and we talked about Spark streaming, there's also Kafka and Apache for streaming data coming in. And Kafka is a distributed streaming platform to store and process streams of records. And it's written in Scala. Builds real-time streaming data pipelines that reliably get data between applications. Builds real-time streaming applications that transforms data into streams. So it kind of goes both ways on there. So Kafka uses a messaging system for transferring data from one application to another. So we have our sender, we have our message queue, and then we have our receiver. Pretty straightforward, very solid setup on there with the Kafka. Apache Storm. Storm is a processing engine that processes real-time streaming at a very high speed, and it's written in Clojure. They utilize the function-based programming style of Clojure, and it's based on Lisp, to give it the speed. That's why Apache Storm is built on there. So you could think of Kafka as a slow-moving, very solid communication network, where Storm is looking at the real-time data and grabbing that streaming data that's coming in fast. So it has the ability to process over 1 million jobs in a fraction of seconds on a node. So it's massive. It can really reach out there and grab the data. And it's integrated with Hadoop to harness higher throughputs. So this is the two big things about Storm. If you are polling, I think they mentioned stock coming in or something like that, where you're looking for the latest data popping up, Storm is a really powerful tool to use for that. So we've looked at a couple more tools for bringing data in. We probably should talk a little bit about security. Security in Hadoop has the Apache Ranger and Apache Knox are the two most popular ones. And the Ranger, the Apache Ranger is a framework to enable, monitor, and manage data securities across the Hadoop platform. So the first thing it does is it provides centralized security administration to manage all security-related tasks. The second thing it does is it has a standardized authorization across all Hadoop components. And third, it uses enhanced support for different authorization methods, role-based access control, attribute-based access control, etc. So your Apache Ranger can go in there, and your administrator coming in there can now very easily monitor who has what rights and what they can do and what they can access. So there's also Apache Knox. Knox is an application gateway for interacting with the REST APIs and the UIs of Hadoop developers. And so we have our application programmer interfaces, our user interfaces, and we talk about REST APIs. This means this is looking at the actual data coming in, what applications are going on. So if you have an application where people are pulling data off of the Hadoop system or pushing data into the Hadoop system, the Knox is going to be on that setup. And it delivers 3 groups of user-facing services. 1, proxy services, provides access to Hadoop via proxying the HTTP request. 2, authentication services, authentication for REST API access and web SSO flow for user interfaces. So there's our REST. And finally, client services. Client development can be done with the scripting through DSL or using the Knox shell classes. So the first one is if you have a website coming in and out, your HTTP request. Again, your 3 different services are what's coming in and out of the Hadoop file system. So there's a couple of the security setups. Let's go ahead and take a look at workflow system, the Oozie. And there's some other ones out there. Oozie is the one that's specific to Hadoop. There's also like a Zookeeper out there and some other ones. Oozie's pretty good. Oozie is a workflow scheduler system to manage Hadoop jobs. And so you have a workflow engine and a coordinator engine. So it consists of 2 parts, what's going on and coordinating what's going on. And directed acyclic graph DAGs, which specifies a sequence of actions to be executed. These consist of workflow jobs triggered by time and data available. And if you're not familiar with directed acyclic graphs or DAGs or whatever terminology you want to throw at this, this is basically a flow chart. You start with process A, then the next process would be process B when process A is done. And it might be that process C can only be done when process D, E, and F are done. So you want to be able to control this. You don't want it to process the machine learning script and then pull the data in that you want to process it on. You want to make sure it's going in the right order. So these consist of workflow jobs, and they're triggered by time and data availability. So maybe you're pulling stocks in the middle of the night, and once the stock is all pulled, so there's our time sequence. It says, hey, they've been posted on the other websites. They post them usually after the stock market closes, the highs and lows and everything. Then once that data has been brought in, in a time specifics, bring the data in at a certain time. Once the data is available, then we want to trigger our machine learning script for what's going to happen next. And so we can see here we have start, our MapReduce program, our action node, and it begins, and either we have a success, then we notify the client of success, usually an email is sent out, in successful completion. Or we don't have a success, we have an error. Notify client of error, email action node, kill unsuccessful. Termination. And usually at this point they say email action notification, but that's usually a pager system. And so you see all the tech guys running to the server room or wherever, where our pager just went off. We got to figure out what went down. The other one is you just look at the next morning, you go, oh, let's make sure everything went through this morning and check all your successes. With the error, usually it's sent to your pager and your emergency call to open up in the middle of the night and log in. So that concludes our basic setup with the Hadoop ecosystem. So a quick recap on the Hadoop ecosystem. We covered looking at the middle part. We had the Hadoop as a file system and how it stores data across multiple servers. Saves money because it's about 1/10 of the cost of using enterprise computers. We looked at Yarn, cluster resource management, and how that works to hold everything together. And then we looked at a lot of data processing. How does it process in and out of the Hadoop system, including the MapReduce setup, which is the Hadoop Basic in Java. And for that, we looked at data collection and ingestion with Sqoop and Flume. We looked at queries using the scripting language Pig and the SQL queries through Hive. We glanced at Spark. Remember, Spark usually comes installed now with the Hadoop system because it does so much of its own processing. It covers a lot of the data in, real-time data analysis setup on there. We looked at Mahout, machine learning. We looked at Apache Ambari for management and monitoring, kind of your security guard and traffic control. Just like we have Sqoop and Flume, which brings data in there, we looked at Kafka and Apache Storm, which is for streaming data. And then we looked at Apache Ranger and Apache Knox for security. And finally, we took a glance at Oozie for your workflow system. Let's start with an introduction to HBase. Back in the days, data used to be less and was mostly structured. You can see we have structured data here. We usually had it like in a database where you had every field was exactly the correct length. So if you had a name field, it was exactly 32 characters. I remember the old Access database in Microsoft. The files were small. If we had hundreds of people in one database, that was considered big data. This data could be easily stored in relational database, or RDBMS. When we talk about relational database, you might think of Oracle, you might think of SQL, Microsoft SQL, MySQL. All of these have evolved, even from back then, to do a lot more today than they did. But they still fall short in a lot of ways. And they're all examples of an RDMS, or relationship database. Then Internet evolved, and huge volumes of structured and semi-structured data got generated. And you can see here with the semi-structured data, we have email. If you look at my spam filter, you know what we're talking about. All the HTML pages, XML, which is a lot of times is displayed on our HTML and help desk pages, JSON. All of this really has just, even in the last, each year it almost doubles from the year before how much of this is generated. So storing and processing this data on an RDBMS has become a major problem. And so the solution is we use Apache HBase. Apache HBase was the solution for this. Let's take a look at the history, the HBase history. And when we look at the HBase history, we're going to start back in 2006, November. Google released a paper on Big Table. And then in 2017, just a few months later, HBase prototype was created as a Hadoop contribution. Later on in the year 2007, in October, first usable HBase along with the Hadoop 0.15 was released. And then in January of 2008, HBase became the subproject of Hadoop. And later on that year in October, all the way into September the next year, HBase was released, the 0.81 version, the 0.19 version, and 0.20. And finally, in May of 2010, HBase became Apache top-level project. And so you can see in the course of about 4 years, HBase started off as just an idea on paper and has evolved all the way till 2010 as a solid project under the Apache. And since 2010, it's continued to evolve and grow as a major source for storing data in semi-structured data. So what is HBase? HBase is a column-oriented database management system derived from Google's NoSQL database, Big Table, that runs on top of the Hadoop file system, or the HDFS. It's an open source project that is horizontally scalable, and that's very important to understand, that you don't have to buy a bunch of huge expensive computers. You're expanding it by continually adding commodity machines. And so it's a linear cost expansion as opposed to being exponential. NoSQL database written in Java, which permits faster querying. So Java is the backend for the HBase setup. And it's well suited for sparse data sets. So it can contain missing or NA values, and this doesn't boggle it down like it would another database. Companies using HBase. So let's take a look and see who is using this NoSQL database for their servers and for storing their data. And we have Hortonworks, which isn't a surprise because they're one of the, like Cloudera, Hortonworks. They are behind Hadoop and one of the big developments and backing of it. And of course, Apache HBase is the open source behind it. And we have Capital One as banks. You also see Bank of America, where they're collecting information on people and tracking it. So their information might be very sparse. They might have one bank way back when they collected information as far as the person's family and what their income for the whole family is and their personal income, and maybe another one doesn't collect the family income. As you start seeing where you have data that is very difficult to store, where it's missing a bunch of data. HubSpot's using it, Facebook, certainly all of your Facebook, Twitter, most of your social medias are using it. And then of course there's JP Morgan, Chase and Company, another bank that uses the HBase as their data warehouse for NoSQL. Let's take a look at an HBase use case so we can dig a little bit more into it to see how it functions. Telecommunication company that provides mobile voice and multimedia services across China, the China Mobile. And China Mobile, they generate billions of call detailed records, or CDR. And so these CDRs and all these records of these calls and how long they are and different aspects of the call, maybe the tower they're broadcasted from, all of that is being recorded so they can track it. Traditional database systems were unable to scale up to the vast volumes of data and provide a cost-effective solution. No good. So storing and real-time analysis of billions of call records was a major problem for this company. Solution? Apache HBase. HBase stores billions of rows of detailed call records. HBase performs fast processing of records using SQL queries. So you can mix your SQL and NoSQL queries. And usually just say NoSQL queries because of the way the query works. Applications of HBase. One of them would be in the medical industry. HBase is used for storing genome sequences, storing disease history of people of an area, and you can imagine how sparse that is as far as both of those. A genome sequence might only have pieces to it that each person is unique or is unique to different people. And the same thing with disease. You really don't need a column for every possible disease a person could get. You just want to know what those diseases those people have had to deal with in that area. E-commerce. HBase is used for storing logs about customer search history, performs analytics and target advertisement for better business insights. Sports. HBase stores match details in the history of each match. Uses this data for better prediction. So when we look at HBase, we all want to know what's the difference between HBase versus RDBMS. That is a relational database management system. HBase versus RDBMS. So the HBase does not have a fixed schema. It's schemaless. Defines only column families. And we'll show you what that means later on. An RDBMS has a fixed schema which describes the structure of the tables. And you can think of this as you have a row and you have columns. And each column is a very specific structure, how much data can go in there and what it does. With the HBase, it works well with structured and semi-structured data. With the RDBMS, it works only well with structured data. With the HBase, it can have denormalized data. It can contain missing or null values. With the RDBMS, it can store only normalized data. Now you can still store a null value in the RDBMS, but it still takes up the same space as if you're storing a regular value in many cases. And it also, for the HBase, is built for wide tables. It can be scaled horizontally. For instance, if you were doing a tokenizer of words and word clusters, you might have 1.4 million different words that you're pulling up and combinations of words. So with an RDBMS, it's built for thin tables that are hard to scale. You don't want to store 1.4 million columns in your SQL. It's going to crash and it's going to be very hard to do searches. With the HBase, it only stores that data which is part of whatever row you're working on. Let's look at some of the features of the HBase. It's scalable. Data can be scaled across various nodes as it is stored in the HDFS. And always think about this, it's a linear add-on. For each terabyte of data, I'm adding on roughly $1,000 in commodity computing. With an enterprise machine, we're looking at about $10,000 at the lower end for each terabyte of data. And that includes all your backup and redundancy. So it's a big difference. It's like a tenth of the cost to store it across the HBase. It has automatic failure support. Write-ahead log across clusters, which provides automatic support against failure. Consistent read and write. HBase provides consistent read and write of the data. It's a Java API for client access. Provides easy to use Java API for clients. Block cache and bloom filters. So the HBase supports block caching and bloom filters for high volume query optimization. Let's dig a little deeper into the HBase storage. HBase column oriented storage. And I told you we're going to look into this to see how it stores the data. And here you can see you have a row key. And this is really one of the important references is each row has to have its own key or your row ID. And then you have your column family. And in here you can see we have column family 1, column family 2, column family 3. And you have your column qualifiers. So you can have in column family 1, you can have 3 columns in there, and there might not be any data in that. So when you go into column family 1 and do a query for every column that contains a certain thing, that row might not have anything in there and not be queried. Where in column family 2, maybe you have column 1 filled out and column 3 filled out, and so on and so forth. And then each cell is connected to the row where the data is actually stored. Let's take a look at this and what it looks like when you fill the data in. So in here we have a row key with a row ID, and we have our employee ID, 1, 2, 3. That's pretty straightforward. You probably would even have that on an SQL server. And then you have your column family. This is where it starts really separating out. Your column family, you might have personal data, and under personal data you would have name, city, age. You might have a lot more than just that. You might have number of children, you might have degree, all those kinds of different things that go under personal data. And some of them might be missing. You might only have the name and the age of an employee. You might only have the name, the city, and how many children. and not the age. And so you can see with the personal data, you can now collect a large variety of data and store it in the HBase very easily. And then maybe you have a family of professional data, your designation, your salary, all the stuff that the employee is doing for you in that company. Let's dig a little deeper into the HBase architecture. And so you can see here what looks to be a complicated chart. It's not as complicated as you think. From the Apache HBase, we have the Zookeeper, which is used for monitoring what's going on. And you have your HMaster. This is the HBase master, assigns regions and load balancing. And then underneath the region, or the HBase master, then under the HMaster, or HBase master, you have your region server serves data for read and write. And the region server, which is all your different computers you have in your Hadoop cluster, you'll have a region, an HLog, you'll have a store, memory store, and then you have your different files for HFile that are stored on there. And those are separated across the different computers. And that's all part of the HDFS storage system. So when we look at the architectural components or regions, and we're drilling down a little bit, HBase tables are divided horizontally by row. So you have a key range into regions. So each of those IDs, you might have IDs 1 to 20, 21 to 50, or whatever they are. Regions are assigned to the nodes in the cluster called region servers. A region contains all rows in the table between the region start key and the end key. Again, 1 to 10, 11 to 20, and so forth. These servers serve data for read and write. And you can see here we have the client and the get sends it out, and it finds out where that start, if it's between which start keys and end keys, and then it pulls the data from that different region server. And so the region signed data definition language operation, create, delete, are handled by the HMaster. So the HMaster is telling it, what are we doing with this data? What's going out there? Assigning and reassigning regions for recovery or load balancing and monitoring all servers. So that's also part of it. So, if your IDs, if you have 500 IDs across 3 servers, you're not going to put 400 IDs on server 1 and 100 on server 2 and leave region 3 and region 4 empty. You're going to split that up, and that's all handled by the HMaster. And you can see here it monitors region servers, assigns regions to region servers, assigns regions to region servers, and so forth and so forth. HBase has a distributed environment where HMaster alone is not sufficient to manage everything. Hence, Zookeeper was introduced. It works with HMaster. So you have an active HMaster which sends a heartbeat signal to Zookeeper indicating that it's active. And the Zookeeper also has a heartbeat to the region servers. So the region servers send their status to Zookeeper indicating they are ready for read and write operation. Inactive server acts as a backup. If the active HMaster fails, it will come to the rescue. Active HMaster and region servers connect with a session to Zookeeper. So you see your active HMaster selection, your region server session. They're all looking at the Zookeeper keeping that pulse. An active HMaster and region server connects with a session to the Zookeeper. And you can see here where we have ephemeral nodes for active sessions via heartbeats to indicate that the region servers are up and running. So let's take a look at HBase read or write going on. There's a special HBase catalog table called the meta table, which holds a location of the regions in the cluster. Here's what happens the first time a client reads or writes data to HBase. The client gets the region server, the host, the meta table from Zookeeper. And you can see right here the client has a request for your region server and goes, hey, Zookeeper, can you handle this? And the Zookeeper takes a look at it and goes, meta location is stored in Zookeeper. So it looks at its metadata on there. And then the metadata table location is sent back to the client. The client will query the meta server to get the region server corresponding to the row key if it wants to access. The client caches this information along with the meta table location. And you can see here the client going back and forth to the region server with the information. And it might be going across multiple region servers depending on what you're querying. So we get the region server for row key from the meta table. That's where that row key comes in and says, hey, this is where we're going with this. And so once it gets the row key from the corresponding region server, we can now put row or get row from that region server. Let's take a look at the HBase meta table. Special HBase catalog table that maintains a list of all the region servers in the HBase storage system. So you see here we have the meta table. We have a row key and a value, table key, region, region server. So the meta table is used to find the region for the given table key. And you can see down here, our meta table comes in, it's going to figure out where it's going with the region server. And when we look a little closer at the write mechanism in HBase, we have write ahead log, or WAL, as you abbreviate it, kind of a way to remember wall is write ahead log. It's a file used to store new data that is yet to be put on permanent storage. It is used for recovery in the case of failure. So you can see here where the client comes in and it literally puts the new data coming in into this kind of temporary storage or the wall on there. Once it's gone into the wall, then the memory store, mem store, is a write cache that stores the new data that has not yet been written to disk. There is one mem store per column family per region. And once we've done that, we have 3 ACK. Once the data is placed in mem store, the client then receives the acknowledgement. When the mem store reaches the threshold, it dumps or commits the data into H-file. And so you can see right here, we've taken it's gone into the wall then sorts it into the different memory stores, and then the memory stores, it says, hey, we're ready to dump that into our H-files, and then it moves it into the H-files. H-files store the rows of data as stored key value on disk. So here we've done a lot of theory. Let's dive in and just take a look and see what some of these commands look like and what happens in our HBase when we're manipulating a NoSQL setup. So if you're learning a new setup, it's always good to start with, where is this coming from? It's open source by Apache. And you can go to hbase.apache.org and you'll see that it has a lot of information. You can actually download the HBase separate from the Hadoop, although most people just install the Hadoop because it's bundled with it. And if you go in here, you'll find a reference guide, and so you can go through the Apache reference guide. And there's a number of things to look at, but we're going to be going through Apache HBase shell. That's what we're going to be working with. And there's a lot of other interfaces on the setup, and you can look up a lot of the different commands on here. So when we go into the Apache HBase reference guide, we can go down to read HBase shell commands from a command file. You can see here where it gives you different options of formats for putting the data in and listing the data. Certainly you can also create files and scripts to do this too. But we're going to look at the basics, and we're going to go through this on a basic HBase shell. And one last thing to look at is, of course, if you continue down the setup, you can see here where they have more detail as far as how to create and how to get to your data on your HBase. Now, I will be working in a virtual box, and this is by Oracle. You can download the Oracle virtual box. You can put a note in below for the YouTube, as we did have a previous session on setting up virtual setup to run your Hadoop system in there. I'm using the Cloudera Quick Start installed in here. There's Hortons. You can also use the Amazon Web Service. There's a number of options for trying this out. In this case, we have Cloudera on the Oracle VirtualBox. The VirtualBox has Linux CentOS installed on it, and then the Hadoop has all the different Hadoop flavors, including HBase. And I bring this up because my computer is a Windows 10. The operating system of the VirtualBox is Linux, and we're looking at the HBase data warehouse. And so we have 3 very different entities all running on my computer. And that can be confusing if it's the first time in and working with this kind of setup. Now, you'll notice in our Cloudera setup, they actually have some HBase monitoring. So I can go underneath here and click on HBase and master, and it'll tell me what's going on with my region servers. It'll tell me what's going on with our backup tables. Right now I don't have any user tables because we haven't created any. And this is only a single node and a single HBase store. So you're not going to expect anything too extensive in here, since this is for practice and education and perhaps testing out package you're working on. It's not for really, you can deploy Cloudera, of course, but when you talk about a quick start or a single node setup, that's what it's really for. So we can go through all the different HBase, and you'll see all kinds of different information with Zookeeper if you saw it flash by down here, what version we're working in, since Zookeeper is part of the HBase setup. Where we want to go is we want to open up a terminal window, and in Cloudera it happens to be up at the top. And when you click on here, you'll see your Cloudera terminal window open. And let me just expand this so we have a nice full screen. And then I'm also going to zoom in. That way you have a nice big picture and you can see what I'm typing and what's going on. And to open up your HBase shell, simply type HBase shell to get in and hit enter. And you'll see it takes just a moment to load, and we'll be in our HBase shell for doing HBase commands. Once we've gotten into our HBase shell, you'll see you'll have the HBase prompt information ahead of it. We can do something simple like list. And this is going to list whatever tables we have. And it so happens that there's a base table that comes with HBase. Now we can go ahead and create, and I'm going to type in just create. What's nice about this is it's going to throw me kind of a, it's going to say, hey, there's no just straight create. But it does come up and tell me all these different formats we can use for create. So we can create our table and one of our families. You can add splits, names, versions, all kinds of things you can do with this. But let's just start with a very basic one on here. And let's go ahead and create, and we'll call it new table. Let's just call it new TBL for table. New table. And then we also want to do, let's do knowledge. So let's take a look at this. I'm creating a new table, and it's going to have a family of knowledge in it. And let me hit enter. And it's going to come up. It's going to take it a second to go ahead and create it. Now we have our new table in here. And so if I go list, you'll now see table and new table. So you can now see that we have the new table and of course the default table that's set up in here. And we can do something like describe. We can describe, and then we're going to do new TBL. And when we describe it, it's going to come up. It's going to say, hey, name, I have knowledge, data block encoding none, Bloom filter, row, replication scope, version, all the different information you need. New, minimum version, 0, forever, deleted cells, false, block size, in memory. And you can look this stuff up on apache.org to really track it down. One of the things that's important to note is versions. So you have your different versions of the data that's stored. And that's always important to understand that. We might talk about that a little bit later on. And then after we describe it, we can also do a status. The status says I have one active master going on. That's our HBase as a whole. We can do status summary. And it should do the same thing as status. So we got the same thing coming up. And now that we've created, let's go ahead and put something in it. So we're going to put new TBL, and then we want row 1. You know what, before I even do this, let's just type in put. And you can see when I type in put, it gives us like a lot of different options of how it works and different ways of formatting our data as it goes in. And all of them usually begin with the new table, new TBL. Then we have, in this case, we'll call it row 1, and then we'll have knowledge. If you remember, we created knowledge already, and we'll do knowledge sports, and then in knowledge and sports, we're going to set that equal to cricket. So we're going to put underneath this our knowledge setup. We have a thing called sports in there, and we'll see what this looks like in just a second. Let's go ahead and put in, we'll do a couple of these. Let's see, let's do another row 1, and this time instead of sports, let's do science. This person not only, we have row 1, which is both knowledgeable in cricket and also in chemistry. So it's a chemist who plays cricket in row 1. And let's see if we have, let's do another row 1 just to keep it going. And we'll do science. In this case, let's do physics. Not only in chemistry, but also a physicist. I have quite a joy in physics myself. So here we go. We have row 1. There we go. And then let's do row 2. Let's see what that looks like when we start putting in row 2. And in row 2, this person has knowledge in economics. This is a master of business and how, or maybe it's global economics. Maybe it's just for the business and how it fits in with the country's economics. And we call it macroeconomics. So I guess it is for the whole country there. So we have knowledge economics, macroeconomics. And then let's just do one more. We'll keep it as row 2. And this time our economist is also a musician. So we'll put music. And they happen to have knowledge and they enjoy, let's do pop music. They're into the current pop music going on. So we've loaded our database. And you'll see we have 2 rows, row 1 and row 2 in here. And we can do is we can list the contents of our database by simply doing scan. Scan, and then let's just do scan by itself so you can see how that looks. You can always just type in there and it tells you all the different setups you can do with scan and how it works. In this case, we want to do scan new TBL. And in our scan new TBL, we have row 1, row 1, row 2, row 2. And you'll see row 1 has a column called knowledge, science, time step, value crickets, value physics. So it has information as when it was created, when the timestamp is. Row 1 also has knowledge sports and a value of cricket. So we have sports and science. And this is interesting because if you remember up here, we also gave it originally, we told it to come in here and have chemistry. We had science, chemistry, and science physics. And we come down here, I don't see the chemistry. Why? Because we've now replaced chemistry with physics. And so the new value is physics on here. Let me go ahead and clear down a little bit. And in this, we're going to ask the question, is enabled new table? And when I hit enter in here, you're going to see it comes out true. And then we'll go ahead and disable it. Let's go ahead and disable new table. Make sure I have our quotes around it. And now that we've disabled it, what happens when we do the scan? When we do the scan new table, I hit enter, you're going to see that we get an error coming up. So once it's disabled, you can't do anything with it until we re-enable it. Now, before we enable the table, let's do an alteration on it. And here's our new table. And this should look a little familiar because it's very similar to create. We'll call this test info. And we'll hit enter in there. It'll take just a moment for updating. everything. And then we want to go ahead and enable it. So let's go ahead and enable our new table. So it's back up and running. And then we want to describe new table. And we come in here, you'll now see we have name knowledge. And under there we have our data encoding and all the information under knowledge. And then we also have down below test info. So now we have the name test info and all the information concerning the test info on here. And we'll simply enable it. New table. So now it's enabled. Oops, I already did that. I guess we'll enable it twice. And so let's start looking at, well, we had scan new table. And you can see here where it brings up the information like this. Well, what if we want to go ahead and get a row? So we'll do R1. And when we do HBase R1, you can see we have knowledge science and it has a timestamp, value physics, and we have knowledge sports and it has a timestamp on it, and value cricket. And then let's see what happens when we put into our new table. And in here we want row 1. And if you can guess from earlier, because we did something similar, we're going to do knowledge economics. And then it's going to be, instead of, I think it was what, macroeconomics, it's now market economics. And we'll go back and do our get command and now see what it looks like. And we can see here where we have knowledge economics. It has a timestamp, value, market economics, physics, and cricket. And this is because we have economics, science, and sports. Those are the 3 different columns that we have, and then each one has different information in it. And so if you manage to go through all these commands and look at basics on here, you'll now have the ability to create a very basic HBase setup, no SQL setup, based on your columns and your rows. And just for fun, we'll go back to the Cloudera, where they have the website up for the HBase master status, and I'll go ahead and refresh it. And then we can go down here and you'll see user tables, table set 1, and we can click on details, and here's what we just did. It goes through, so if you're the admin looking at this, you can go, oh, someone just created new TBL, and this is what they have underneath of it in their new table in there.
And with that, we have come to the end of this crash course video on Hadoop. I hope it was informative and interesting. If you have any questions related to the Hadoop topics that were covered in this video, then please ask away in the comment section below. Our team will help you solve your queries. Thanks for watching, stay safe and keep learning.
Hi there, if you like this video, subscribe to the Simplilearn YouTube channel and click here to watch similar videos. To nerd up and get certified, click here.